always find me on Twitter and Telegram or LinkedIn or whatever you want, or just email me, bruno@web3.foundation. If you have any questions about this presentation or anything else regarding Polkadot, Kusama, Substrate, our whole ecosystem, anything at all, I'm always at your disposal to answer any questions. So at Polkadot, we believe in a decentralized and fair internet where users control their own data. Where users also control their own identity and their destiny. And to do this, we need a free, open, decentralized, and censorship-resistant Web 3.0. And to do that, we are building a suite of blockchains in a way which will let other blockchains connect to each other. Now, in order to, this is the link that I mentioned in the intro, but if you haven't gotten through it, please go to bit.ly/polkaprep. This will prepare your entire environment on your computer to compile and build these tools that we'll be playing with. So in our mission to decentralize the web, we've built this Polkadot blockchain, which allows other blockchains to connect to it and to talk to each other through it. There are quite a few projects that claim to do the same thing out there today. The difference in this case is that Polkadot's connected chains share their security, where in other shared blockchain systems, you may have a problem of the whole ecosystem being only as strong as the weakest chain. Because imagine for a second, if the weak chain sent a message to a more secure chain, and that message includes something like increase that user's balance by 1 million coins. If that weaker chain then gets hacked or reverted or forked or something, what happens to the more expensive chain? Well, that chain is in trouble, right? Because it doesn't know which version of the past to trust. And so that makes the whole system only as secure as that weak chain. In Polkadot, every chain that connects to the ecosystem is as strong as every other chain. This is possible because they're all connecting to the relay chain, which is the master chain coordinating everything between the master chain. The relay chain has these validators, and the validators are validating random connected chains at random periods and giving them finality. So the chains that are connected to Polkadot, they get their finality. They produce their own blocks, but they kind of seal those blocks into finality through the help of the validators on the relay chain. So the entire system is only as secure as every other chain. And the more chains are connected, the more secure the system is. The more validators there are, the more secure the system is. But this sounds really complicated, right? How are all of these chains connected to each other? And how is this relay chain built at all? Well, this is built by the development company Parity from Berlin, which has built plenty of blockchains for enterprise users and other use cases before. And they realized at some point that they were repeating a lot of the work that they were doing. They were constantly reinventing the database, the networking, the consensus layer, the transaction queue, and a lot of these other things that blockchains typically need. So they decided, why not abstract all this, and why not just turn the knowledge that we have into a framework? Why not build a common starting ground from which we will build all of our future blockchains? We'll do that really well. We'll improve that. We'll let it out into the open for others to build on as well. And we'll have a really solid base so that people who are building blockchains don't have to spend 2 years researching and doing who knows what kind of research and development. Rather, they get this database, they get the consensus, they get the common pieces, and they can focus on their application logic right off the bat. And that's really powerful, right? So Substrate came to be from this idea. And Substrate is an open source, modular, and extensible framework for building blockchains. That's all there is to it. It's just like a template for building blockchains. Think of it as your blockchain's bootstrap. So Substrate provides the core things that I just mentioned. So that's the database layer, that's the networking layer, the consensus engine, the transaction queue, and a library of runtime modules, which we'll go through next. And each of these modules can be extended and customized to your liking. So you can be as specific in your application logic as you want. Your chain can be as application specific as you want it to be. And one of the key selling points of Substrate is its runtime. The runtime is composed of these different palettes, and these palettes are part of this system called Frame. these palettes are Rust modules that have certain functionality, but that functionality is encapsulated in that palette. It doesn't leak elsewhere. So it's all very Lego blocky. You can connect all of these functionalities together into one common runtime that then makes sense and is useful for you and for your blockchain. So how does that work? Well, for example, you can see up here in the circle, that's one runtime, right? And that runtime contains the palette system, babe, pseudo, grandpa, indices, timestamp, balances. These are all different palettes, and they're marked with the pink border in the table below. But there are many other palettes as well, and these are not all of them. These are just some of them. But for example, if you want smart contracts in your chain, you would add the contract palette in there, and then you would rebuild. And when this recompiles, the new binary will contain the smart contract functionality. Your chain will automatically have smart contracts built in. So why is this special? This is just adding features, right? Well, it's special because of WebAssembly. And WebAssembly is something is like this binary code format which takes up very little disk space and very little memory. And the advantage of this is that it can be executed in a wide variety of environments, even the browser. Why is this important? Well, because this runtime, when we build it, when we compile this circle of things, it results in a WASM blob, a WASM file, a WebAssembly file. And that file has, along with the native file, along with the binary that you get from compiling the Rust, so you get a program that you can run, that contains the runtime. But along with that, you get this WASM file that also contains the runtime logic. And this WASM file contains all the logic that a blockchain needs to progress from one block to the other. So this contains all of the rules that the blockchain needs to be built, to continue building itself. And substrate-based chains all have this common functionality. They will all produce this WASM blob. And this WASM blob is stored on the blockchain itself. So why is this important? Well, previously, whenever you needed to upgrade a chain, like for example in Ethereum, if you wanted to change some opcodes or something at the core level that would change the gas mechanics, if you wanted to add new crypto primitives into the chain or something, you would have to hard fork, right? You would have to develop this functionality, add it into the clients that are out there, and then you would have to get everybody who's running a node, who's running an Ethereum client, to upgrade that client to the new version. And everybody who didn't upgrade would be left behind on an outdated fork, which is no longer the canonical fork. You would have to get in touch somehow with everybody who's running your node, which is difficult in a system where most people who run your nodes are anonymous. And they would have to be aware or actively pursue updates and be aware of changes that are coming so that they can jump in and do this on their own. And that's an arduous and frustrating process for any hard fork coordinator, especially in a world where we are still communicating through centralized media about upgrading decentralized technology, right? That means that anybody who would just stop, if Google decides to no more like discussions about this, it's very difficult to reach those people. And we have like maybe one or two platforms through which we communicate. That's GitHub, that's Twitter, and that's maybe Google. And we rely on these platforms to communicate to everybody. Obviously, that's not sustainable long term. If you look at it from a kind of an absolutist kind of view, like we want to decentralize to the maximum. So what substrate-based chains allow you to do is they store this WASM blob on the chain itself. That's like maybe a couple hundred kilobytes. And it contains all of the logic. And now, when you're running a substrate-based client, so a node of a substrate-based chain, any chain, that node is reading data from the chain. And it also reads in that WASM blob that's on the chain. And it looks at the version of the runtime that's written inside that WASM blob. And it compares it with the version that it has locally in its own native code, in its binary. If those versions are the same, it will run the native code, the binary, because the binary is always faster than WASM. WASM needs to be interpreted, executed, and so on. So it's orders of magnitude faster to run this locally, like bare metal and the native Rust code. But if the WASM code's version is newer, then the client will use that. It will download that new WASM code that's on the chain, and it will treat that as the canonical runtime that it's supposed to execute. And while it will be slower to run, it'll use a little bit more resources of your computer, your node will actually upgrade itself. So if you replace that WASM blob on chain, that chain will upgrade itself while it is still running without you actually having to tell anybody to install a new node, to download new software, to replace their software that's running, and so on. This is extremely powerful. You basically get forkless upgrades. You basically get the ability to upgrade a blockchain with new functionality without having to talk to a single person except those in charge of changing that WASM blob. Now, how that change occurs, there are two different ways. One is through the sudo module, and you can see it here in this runtime. The sudo module is included. Now, the sudo module is just like an admin module that lets you execute any function of the chain at any time from one single key. So that's like an admin key to the chain. And this is often useful when a chain is just launching, so that you can do fast incremental upgrades without having to go through on-chain governance to vote for these changes, right? So with sudo, you can just replace that code and it'll go into effect immediately. The other way, which is the decentralized way, which you deploy after you're done with sudo, and after you're fairly certain that all of the kinks have been ironed out, is the on-chain governance way. And the way you do this is every token holder of every substrate-based chain has the right to vote on decisions that we call referenda. And these referenda can be anything from changing a simple value of the chain, like the maximum number of validators who are allowed to validate, to the complete replacement of the WASM blob for the runtime. So when I have some new functionality that I want to deploy into a chain, say for example, Polkadot is running right now. And right now in Polkadot, you cannot transfer dots, the native tokens. That's by design, because there's still the sudo module. The chain is still in like early launch phase. And during this phase, we definitely do not want to enable people to speculate with tokens. We don't want to endanger any economics of anything of the chain. And so the transfer functionality is disabled for good until the community enables it. And the community alone can enable it. The sudo module will be removed and replaced by the democracy module very soon. And what's going to happen is the community, every dot holder, will be able to trigger the function, the runtime change, to allow balances to occur, to allow balance transfers to occur. And when they propose this, other people will be able to vote on this decision. And there are some mechanics on how to prevent plutocracy and how to make sure that the election is fair, and how to make sure that the voting is, both and Sybil resistant and bribe resistant and so on. So that's a topic for another time. But the democracy is fairly fleshed out. We've been running this on a sister chain called Kusama for 8 months now, and it's worked fairly well. We have made over 100 runtime upgrades already and many different other types of upgrades, and the chain is progressing very nicely. So it's like an early release of Polkadot that's existed for 8 months now. So that it's verified to be working. But what matters here is that this forkless upgrade mechanism is available to every single substrate chain. Every single blockchain that builds on substrate has this ability to make an upgrade to itself without having to hard fork. You can, of course, hard fork. That's always an option, but you don't have to. You can avoid that nightmare of coordination now by executing these updates on chain. So what happens when the node takes the new WASM blob from the chain? It loads it in, it starts running it, and then it's up to the node operator, to the one running this client, the software, to upgrade when they feel like upgrading. They don't have to do it, they can do it, they can do it whenever they want. The only thing that's in it for them if they do is a bit better performance, right? The node will run native code, because when they upgrade the client, the versions of the runtime will again match, and the client will no longer run the WASM blob, it will run the code that's native. So the native code will be equal to the code in the WASM, and the client will be running the code natively in a much faster way, so some performance to be gained there. This is important for validators, but for barely anyone else. So if a validator cares about performance, and they should, then they will of course keep track on the updates that are coming out and upgrade nodes whenever they feel safe about upgrading, like maybe wait a day or two after release to see if everything's fine and so on, and then upgrade as soon as they can, because not upgrading can make them slower than other validators, and then they might lose out on some rewards, right? But that's basically why they would want to do it. So in this workshop, what we're going to do is we're going to play with the substrate node template. And the node template is a working substrate node. It's like a very basic chain prepared for your experiments. And it's actually what most blockchains start out with when they're building their blockchain. So most of them start out with this and then build custom functionality on top of this. This is like the base starter kit. So Substrate is the framework that enabled the node template, right? Substrate is just a set of code that allows this to happen. So the node template is something you modify and turn into something you want. So we will have the sudo module in here, so we will be able to execute administrative functions through an unlocked and very rich account that will be that will summon through the dev flag. So we'll run a development chain which will have this account unlocked, and we are also going to build a custom palette for this chain, so a custom module that will allow us to do some very application-specific logic, so that you can see how easy it is to customize a blockchain that you built on Substrate. We will also be using Polkadot.js apps, and that's a official front end for interacting with Substrate-based chains. The beauty of Substrate-based chains is also that because of the way they're built, because of this framework, every Substrate-based chain exposes a bunch of metadata from its runtime. And this metadata is available to any client that connects to that node. And this metadata will contain information on all the events, all the errors, all the functions, every single thing that the chain can do, all the constants, everything will be in this metadata, ready for consumption by any connecting client. And this is kind of like if you're familiar with Ethereum and there's smart contracts and you have the ABI. So the ABI is like an interface, a JSON file, a JavaScript file, a JavaScript object file, which just defines which functions and values exist in this smart contract. And this is similar. So a Substrate node will expose this metadata about itself, and a UI will be able to customize itself based on this metadata. And polkadot.js.org/apps is one such UI. So this UI is generic. It lets you access any Substrate-based chain, and it will modify itself according to the modules that this chain has. For example, if you visit Polkadot through this chain, you will see all the regular functionality in there. But if you switch the connection to Edgeware, which is a smart contract chain based on Substrate, you will get a different layout, a different color, and the menus will now contain the option contracts, where you will be able to interact with smart contracts, which is not present in Polkadot or in Kusama when you connect to those. So the UI can self-modify based on the metadata that is being fed to it from the chain itself. And that's really powerful as well, because it lets you build generic wallets for all Substrate chains, right? And imagine how powerful that is. So we'll also be dealing with the Substrate front-end template. Now, Polkadot.js org apps is a behemoth, right? It's a big application suite that contains every single possible function, like in a simple button format. It literally contains, it's for power users, basically. It contains everything you can do to interact with a Polkadot, with a Substrate-based chain. And it's too much for everyday users. That's why we have, and it's also very heavy to build. It results in a huge website that uses a lot of memory and so That's why we have the substrate frontend template, which is a lightweight React-based template that lets you interact also with any substrate-based chain, but in a very primitive manner. This is something like it's going to look there. So we'll get a bunch of unlocked accounts. We will see our blocks. We will see our balances, and we'll be able to interact with different palettes inside of our runtime, as you'll see. Now, what's important to know when developing palettes and when customizing substrate-based chains, we will be making heavy use of macros. And macros are like magic, magical code that expands into more code. So macros let you write very little code that becomes much more code during compilation. For example, if I make a macro that lets me type the number 2 and then plus and then maybe the asterisk button and then the number 7. During compilation, that macro could expand that little symbol to mean that the number 2 pluses itself, like 2 plus 2 plus 2 plus 2, 7 times, right? Stupid example, but that's how this code expansion in macros works. And so we'll be using 4 main macros that everybody uses when they expand substrate-based chains and the node template into their own application chain. Those are declare storage, declare module, declare errors, and declare event. Declare storage is used to tell the chain how you want to save your data. That's it. It just tells the chain which prefix to use in the data tree and how to fetch that data, how to save it. The declare module is like the main body of the palette. It's like the main part. Inside it, you will put all your functions and various other declarations that go, it's just the meat of it, it's the logic. Declare event will list all of the events your palette can emit. And an event is like if you send a balance to somebody, excuse me, if you send a balance to somebody, the transfer event is emitted. And anybody who's reading data from the chain can listen for events instead of reading the blocks and parsing the data inside the blocks. And declare error does the same thing for errors. Any error you can encounter while using your palette will be documented in declare error. So we can actually, so the basics of runtime development in Rust here. It's important to note that in substrate-based chains in general, there's no such thing as a rejected and reverted transaction. So transactions always leave an effect on the chain. And they will always charge a fee for doing anything, even when a transaction is invalid. So if, for example, you have 1 dot and you try to send 1 dot, it's going to reject that sending because you didn't leave enough room to pay for the fee. But it's still going to charge you the fee for the attempt because it has to leave a mark on the chain that you tried this and that it failed. Whenever you issue a command to the blockchain, you submit what's called an extrinsic. And an extrinsic is just like an outside input into the chain. And this chain will make a log of this attempt. And all of the extrinsics, failed or successful, will be logged in the blocks of this chain. And that's why you're charged. And that's why you should keep in mind how to develop these modules. So you always have to keep partial state changes in mind, right? You can't really rely on the module to revert your transaction if it only went halfway. So you have to build your logic in a way that will fully revert if something failed, or that will execute only when all the sanity checks have passed. That's a caveat that you have to be aware of. So this is the basic layout of a module. We'll do imports at the top. We'll define the trait, and that's just where we put our common types and so on. And then we have our macros into which we'll put the logic. this is how we declare storage. Actually, let's get into the meat of things and start developing, because we are going to run out of time otherwise. So let me just skip out of this one and fire this up. So we have here the substrate node template. I hope it's big enough to read, and this as well. Okay. So if you've gone through the prerequisite guide to set things up, you should have this up and running. The node template you can compile with the command cargo build release. And so it didn't do anything for me because I didn't do any changes. I just compiled this a while ago. Now, compiling takes a while, especially if you're starting from scratch. The good thing is that if you're only changing some files, it'll only recompile those files. So it'll actually be much faster when you make little changes. But the first compilation might take a while. It takes 10 minutes on my desktop rig. It can take up to 40 minutes on a laptop. It'll depend on your machine. But luckily, you only have to do this once when dealing with a specific node. So if you go into palettes here, you will see the template subdirectory. Now, the template palette is actually the one that's included with the node template by default. This is something for you to hack on. This is here as an example. And the files that we'll be modifying are in source librs, so that's the meat of our module, and cargo.toml, which defines our dependencies, the packages that we need to pull in. But before we do that, let's check this chain out, shall we? So I'm now in the folder of this node template, and you run it by running just /target release. So every build will get put into target release, and then the binary in this case is called node template. You can run it by just doing this, but it's not going to work, because if you do this, this is not a development chain, and it's going to expect a validator. It's going to expect actually two validators. So you would have to run two nodes that connect to each other to produce blocks, and it wouldn't work. It wouldn't move. But if I do dev, it's going to run a development chain that just produces its own blocks and does its own transactions and has some unlocked accounts for you to play with. So this is great for testing your logic locally. And then when you're ready to deploy, then you just remove dev. It'll start a new chain in a new location with a new database, and you can distribute that binary to anybody you want to run your node, and then you'll have a blockchain. But for now, let's just run it with dev. You can see here that it is now working, and every time it makes a block, it'll send you all of these messages. Now, my Unicode characters are a little bit broken in this Bash emulator here, but if you're using something native like Linux or Mac OS, you will see beautiful emoticons here being output in your logs. This is just a Windows issue for me. So now the chain is running, and a substrate chain by default listens on port 9944. So let's open that up. Let's actually use our substrate frontend template. And again, if you went through the prerequisites post, you will have this folder here, substrate frontend template. And the frontend template can be started with just yarn start. So now it's starting this development server, and it's running the page for me. And this page will automatically connect to localhost 9944 so that it can read our blockchain. Connecting to substrate, there we go. So what can we see here? Let me zoom in a little bit. All right. We can see here that we have some accounts, and we can switch between them. This is the account from which we are acting. So this is the one we are logged in as. The metadata that I mentioned that's being exposed by every substrate chain can be seen with show metadata. And you can see here it's just a JSON file, and it's quite big, right? That's because it contains literally everything the chain can do. So let's try and find in this whole mess our template module. And actually, let's look at what the template module contains. So in this case, it contains like out of the box, it comes with some definitions. It comes with some, this we'll explain later. It comes with some imports. It comes with a trait definition that enables events. This is just boilerplate for enabling events. It comes with a definition for storage, so it stores something. And it comes with a definition for an event, that the event screams that something was stored. And it also has some errors here. And then there's the meat of the module. So I'm not going to go through this because we'll go through it when we'll be coding. But we have two functions in this module. One is do something, and the other is cause error. And this will just demo an error. You will see what an error looks like. So the error still changes the state of the blockchain, but it errors out for the user. And this function will just store a random, some data that you save into the chain, and you will be able to fetch it back out. So, sorry. Yeah, so actually let's demo this right away. So we have here the function called do something. Let's try and find it in our metadata. There we go. So we have a call that's do something, and that expects a unsigned integer 32-bit. So something, it expects an argument called something. And the documentation is here. So anything you write in a, whoops, wrong one. Anything you write in behind a triple slash above a function becomes its doc block, becomes its documentation. And that's why we can see this here in the metadata. The documentation is here, just a dummy entry point, blah, blah, blah. And this is how you actually add documentation to your metadata as well, so that the various UIs that connect to it can actually present it to the user. So let's try and interact with this chain. It's already on block 40 with the finalized block at 38. Pretty cool. So we have these accounts here unlocked with a bunch of coins, and we have these other accounts here that just don't really matter. These are from my Polkadot.js extension. So if you install the Polkadot.js extension, you'll be able to keep your keys in this extension. And so this will let you connect to various Web3 websites. So websites that interact with substrate-based chains, you'll be able to interact with them. Okay, let's first demonstrate a simple transfer of units. So let's demonstrate. Let's find. So Alice will be sending to Bob. Let's copy this address. Let's put it in here, Bob, and let's put 2 million. So this 1 unit is all of this because we are showing this with the smallest possible unit with planks. So we'll send 2 units over. Submit. And now it's being submitted. There we go. It passed. So transfer succeeded, and there we go. Sorry. This is our event. Balances, transfer event happened. From account to account, how much? And there we go. And it's finalized. Wink. So we get an event when it's included in a block, and then we get another one here, notification, when that has been finalized. Of course, there's no change here because these are millions and we just sent 2 units, so nothing there. Now, we said that we have this template module, right? And the template module has some functions. And the template module has 2 functions. Do something and create error, or whatever it was called. And cause error, yeah. So let's check it out. We can interact with a palette by building an extrinsic ourselves. So we find the palette that we're looking for. There we go, there's a template module. And we suddenly see, you see, it automatically offered only the functions in that module. And that's because of the metadata. So the metadata just was parsed for this, and now it offers me only these 2 functions. So let's cause an error. Now let's submit. There we go. So this extrinsic failed, that's an error, and we got a dispatch error, right? So we got the information about this error that occurred. But if we do something, let's put in 5. There we go, something stored, success, just a dummy event. So we got the event that something was stored. And now, look at this. So this UI here is a custom UI developed just for this node template as a demo. And that's for this substrate frontend template. And we'll be modifying that later for our use case. So we now have the current value here at 5. Now let me demonstrate that forkless upgrade that I was talking about. So we go to substrate node template. And now notice that our chain is still running, right? Our chain is still running. I'm not going to turn it off. And what I'm going to do now is like this. So we are going to rename this into cause an error. Insignificant change, but it's changed nonetheless. It should be visible. So now we will go to runtime of the chain itself of the. So there's this parent runtime that loads all of the palettes templates, and we need to change some information in this parent runtime. There we go. You're looking for spec version. So if you change spec version to this and then recompile, the WASM that is the result of this compilation will be different from what is running natively. And then the chain will actually grab the WASM from the chain and run that. Let's try that out. Hopefully it works. So now we've saved this. We have changed our function and we have upgraded our spec version. Now we need to recompile. So we'll open a new tab for this. There we go. And now just a typical cargo bolt release. Now notice that it only starts from like the very end. So the last 4 modules it needs to rebuild. So it's going to be fairly, quite a bit faster than it would have been starting from scratch. You can see that this 728, this means this is how many crates it has to build. So how many modules it has to build, compile, in order to get to the final one that we are using. That's a lot. So that takes a while. But in this case, it'll be done much faster because it only needs to do the ending, the final part. Okay. So while that's happening, let's also start with. We can't really start with this just yet because it's compiling, but let's try and do. Okay, well let's go through some basics. I think it already went past the sensitive parts. Yeah, let's explain some things. All right, so at the top here you saw this line. So this is also just copy-paste friendly. You will be copy-pasting this. You will never be typing this out from scratch. Actually, most of this stuff you'll never be typing it out from scratch because it's all boilerplate that you can use. But it still warrants explaining. So in order to build substrate-based chains, you cannot use the Rust standard library because that's big and that would be too big to include as a WASM blob. So there's this no standard mode, and all this really means is that sorry. All this really means is that when you're not using the standard feature, then activate the no standard mode. This is just something you include in every module that you build because you want this standard Rust module mode to be disabled. Otherwise, the WASM compilation is just not going to work. It's not gonna complete. What else? This here is interesting and should be familiar from other languages. So you just import the things from Substrate. So these are the code that we want to share. So this is the framework's code that we want to reuse. So we import frame support, and then from frame support we import all of these macros that we'll use. So declare module, declare story, declare event, declare error, and dispatch, which you don't actually need to import it otherwise here. From frame system, we'll also import itself because the system will let us access some system level values like the block number, for example, and a macro that makes that lets you ensure that something is signed, right? Actually, not a macro, just a function. So whenever you submit something from outside of the chain, like the extrinsic, that has to be signed in most cases. There are some non-signed extrinsics that you can submit. That's a miscellaneous use case. But in most cases, you need a transaction to be signed. So you need it to be signed with the private key of a wallet that somebody is interacting with the chain. This function will just let you extract who the signee is if he exists. If he does not, an error will happen. So that's what this function does. It's like a shorthand convenience method for checking that a call is signed. Okay, this is done. So let's take a look if we can make this work. You can see here that we already have an upgrade runtime shortcut function. I wonder if this works. I've never used it. Let's see. So we need to find the WASM file here. All right, no template. So the WASM blob will be in target, release, wbuild, node template runtime, and there it is. Node template runtime compact WASM, and this is the file that you need to upload. So if we upgrade this, let's see what happens. So we just saw two events happen. Code was updated. That means our upgraded code was successful, and a sudo just took place. So we got an event that an admin did this. So this little module here, this little component in React that somebody built, this already applies this sudo call to our forkless runtime upgrade node. And let's actually see if this works. Now, right now it's not gonna, but if we refresh, it should. Let's template module. Cause an error. There we go. So now our function is called differently. It has a different name, and we did all of this without even restarting our chain. The binary is still chugging along. And why is this possible? Because it just downloaded the WASM from the chain, and it's running on that. And that's why the function name changed, and our runtime upgrade was successful. We didn't brick the chain. We didn't need to hard fork. We didn't even need to upgrade our built binary. We didn't need to do anything, and it just worked. So if we wanted to do this manually, like without this shorthand convenience component, we could do this through the palette interactor as well. So we could pick the sudo, and we could pick sudo unchecked wait. So this unchecked wait function is what you would call when you're doing the forkless update. It's slightly more complex. This is why it's abstracted here in this part. And then you have the call, which needs to be encoded, and then you need to add the wait, which you expect. So wait is like if you're familiar with gas in Ethereum, that limits how many calls can fit in a block. This is wait here. So wait is let me show you in code. You can see above a method here, wait equals 10,000. So there's a limit of wait per block, and like any function call that exceeds that limit is not going to make it into that block. It'll be queued up for the next one. So it's very similar to gas. I should note that this only takes into account the time to execute the function. So this is CPU time. Waits are based on CPU time and the cycles that it consumes, but it's not based on transaction size, so it doesn't take into account state growth and stuff like that. So this is just computationally how much it costs to execute a block. And there are some benchmark tools that you can use when you're building your own palette, how to benchmark your functions to be in line with the weight that we expect. You need to be within a certain limit, or otherwise you are going to have trouble including your transactions. And also, some processing might be so heavy that your validators will start lagging behind, right? So if you leave unchecked wait, then you might apply too much for the validator to process quickly if there's too many heavy function calls. And this can interfere with block production. So this is why the wait system is there, to limit this whole CPU processing per block to a reasonable number. Anyway, I can't really fill this out off the top of my head, so I can't demonstrate this. But then what would happen is, when we fill this out with some data, I don't know, whatever, we would click sudo, right? And then sudo would execute the sudo module. So only the sudo command will invoke the sudo powers of our Alice account. Alice is the sudo. When you run the dev chain, Alice is the sudo account. The sudo button would invoke the Alice sudo powers to call this combination of extrinsics and produce the same result as this upgrade runtime thing did for us. Now let me show you something else. Actually, we are kind of running out of time, so let's go into building the custom thing. Let's delete everything from lib.rs. And don't worry, I'm going to share a written version of this tutorial after the workshop with you, so you can follow along with this at your own pace. You don't have to rush along with it. Let's check it out. So like I said, you will first have to import some things, right? So we have here the configuration flag for no standard, and that's just always has to be there. Then we are importing some macros, and here I have changed it to include also the ensure macro, and the ensure macro just is like an assert. It's like make sure what we put into parentheses is true or emit an error. And we need the storage map to store some values into our chain. Now, what we're going to be building here is a proof of existence blockchain. A proof of existence blockchain lets you log the existence of a file or some data at a certain point in time with and make it cryptographically verifiable. So if you have like a song and then somebody comes out and says, no, this is my song actually, then if you registered it on the proof of existence blockchain, you can actually prove that you registered it at a certain point in time. That's the point of these. It's like a blockchain notary, right? So we'll do that. So for that, we will need to kickstart our module. And I said that we need to define the trait. And inside the trait, we put this type event. So if you don't, this is again boilerplate code. If you don't put this, your module can't emit events. That's it. And then we have these macros with their fake bodies here that we will be filling out. Let's first put this in. So the module is defined through a struct. So you define this pub struct. Again, this is all, you're going to be just pasting this in. But what matters is that this origin thing, whenever you're building your custom palette, your custom blockchain, the very first argument of every single function inside of that module will be origin, always. And origin is where that transaction is coming from. And that's what we will be ensuring is signed. So origin is the origin of the transaction, and it's always the first argument of every function. Now, to activate these basic metadata sharing functions of our chain, we need to include these two lines as well. So we need to declare a type of error, and we need to set the function of deposit event to be default. Again, boilerplate code, you would be including all of this every time. This just makes it possible for the module to emit errors and events at all. Otherwise, it can't do it. Now, we will need to, because we're storing strings into our blockchain, and I mean, we're storing hashes, and hashes are just strings. We will hash a file, and we'll store it hash, and then we will register that on the blockchain. So a hash is just a string, and since we're storing strings, strings in Rust are represented as vectors of bytes. So we will need a vector structure to use so that we can store vectors. So we'll import that, and we'll import that from the standard palette. We'll import vectors, but we can't just import that without actually adding the dependency in as well. So this is where we will be modifying our cargo toml file. Sorry. Yeah. So let's modify this cargo toml. Let's put it at the bottom here. Okay, and then we will add this. So we have sp_std/std. So now we have this standard library loaded in, and it should work. We can add a comma here. So now we have this dependency. When we build, it'll pull this in. It'll build it for our module. We now have access to our vector, right? So let's now define some events. We said that we wanted to register our file on the blockchain. So there are two events that we could fire. We could fire that if I'm registering a file, I'm registering a claim for that file. So I'm claiming that it's mine, that I registered it. So we can call this claim created and claim revoked. It's very straightforward. So this is how we do events. You have an enumeration, so a list of events where this account ID will become available to us from this trait through the account ID type. And the / above events is again the event description, the event documentation. So when an event is emitted, it will have this description inside it available for reading by any client that connects to it. Again, helping the UIs and helping the wallets build things. So we have two events. One is claim created, and that will emit account ID and a vector of bytes, which will be our hash. And claim revoked will emit the same thing. So anybody listening in can just read this. A caveat here that trips a lot of people up is that event enums and enums in general in these macros, because these macros are not pure Rust code, they're macros. They have some caveats that are designed to minimize falling, shooting yourself in the foot. But sometimes it trips people up. One of those trips is the ending comma, the trailing comma on the enum list. It has to be there. Otherwise, it's not going to even let you compile. So these enums need a trailing comma at the end. Then, so now we have these. These events for claims, right? Now, what kind of error can we encounter in our palette? Well, somebody may have registered this claim before. The claim may not exist if we're trying to delete it, for example, if we're trying to revoke it, or you can try to delete the claim and not own it, right? We don't want anybody to delete anybody's claim. So let's put that in as well. Again, an enum, a list of errors, and messages for those errors are here. Okay. Finally, let's declare the storage, and I'm going to speed up here because I'm running out of time. This is how this works. So you define a trait store for module T, and this part here is important. This is what defines the prefix in the database. And whenever you're building a palette, this has to be reasonably unique among other palettes in your blockchain. Because if they share this, they will share a prefix in the database. This is going to get hashed as a prefix, and the data is going to get appended to it. So if I name this foo and somebody else names it foo, names their storage item foo, then our data will clash, and that's not good. So make this as unique as you can every time. No need to do random numbers or something, but if you just call it like your palette, should be enough if people are mindful to look into what kind of palettes they're including in their chains. This is the name of our storage map, and that's going to be a map of hashes, and these hashes are going to be hashed by Blake2 128 concat hashing algorithm. This is the default, but it has to be verbose. You have to express it like this. Again, very copy-pastable. And these hashes will map to tuples of account ID and block number. So we're going to store account ID and block number for every hash that we include. And these hashes are going to be those file hashes. Finally, let's build those functions for our module. I'm just going to paste this in because we are very much out of time. So we now have these functions in here. So we have a create claim function, and we have a revoke claim function. Let me just put this into build mode so that we can maybe attempt to run it, but let me explain it while it's building. So we define a struct for this module. This is again a copy-pastable template. You will be using that. These are the template functions that we included before. Now, these are the individual functions, and you can see that they're heavily documented. This is from that tutorial that I'm going to share with you. So the create claim function is going to do the following. It contains, like I said, the first argument is always the origin, and the second one is the proof, the hash of the file that we're trying to save. So first we'll grab the sender by ensuring that the origin is signed. This here, the question mark, means either return the origin, either return the sender or error. So this just is a one line for give me the sender of this transaction or error out. Then we'll make sure that the proof's storage map does not contain this proof that we're trying to save. If it does, we emit the error that the proof is already claimed. Somebody already submitted it. Then we store the current block from the system module. We grab the block number and we insert this proof into our storage map. You may be wondering why this ampersand here. This is because of a Rust mechanic called borrowing. In Rust, if you send a variable into a function without borrowing, then that variable stops existing inside the context where it was sent from. So we would be unable to use proof if we didn't use this ampersand here, because it would disappear from our context here. But the ampersand means do what you need with this and then send it back. So this is why this happens. And this is why we don't need them here, because we'll no longer use them in the function. This is where the garbage collector can discard them. And so we save this into the blockchain, and then we emit the event that the claim was successfully created. So the revert function does a similar thing, but in reverse. It also checks if the sender is the owner, which we'll go through if we have time. Let me see how this is working. Okay, it's still compiling. So we have here the sender. Again, we grab the sender. We then ensure that proofs exist, that this proof that we're trying to delete exists. And if it doesn't, then we emit an error, no such proof. Then we get the owner of the claim. So we take our proofs storage map and we get. Get is a built-in function in our storage map. So no need to specially define it here in declare storage. This is built in. So we get our proof out of this. But since we are binding our hash to a tuple, so two values, account ID and block number, we would get that tuple here. So the way we extract the owner is we say let and then like this. The first variable that we extract from this tuple will be applied to the owner variable, and everything else will be discarded. This means discard. So it will just grab the account ID stored here. It'll just discard this. We don't care about the block number. And then we ensure that the sender is actually the owner. So we equalize these two. And if not, then we emit an error and we stop the execution. Again, if we stop here, the state of the chain changed so far, and we have to charge the user a fee. So this is still going to cost them some money if they failed. Then we remove the proof from our map, and then we emit the claim revoked event. Okay, let's try and test this out. Hopefully, there we go, it compiled. Now, since I failed to increment the spec version, this wouldn't work as a forkless upgrade. So let's rerun the chain. In this case, we're going to stop the chain and rerun the binary. Now let's try this out. Hopefully this works without purging the chain. But even if we purge it, it's not a big deal. Let's interact with the palette. You can see here that our template palette is, the component is gone. So something is different. Let's see, template module. And we have here create claim and revoke claim. So now if I put in here the bytes, let's say this is obviously not a good file hash, but we'll just put that in. Let's sign it. And we have just created a claim for this file. So we have just claimed this hash. Now let's try to claim this from the Bob account. The same thing, signed, let's see. Failed. All right, so we have failed this claiming because this proof is already claimed. Let's try and revoke this claim from the Bob account. Again, failed. Doesn't work. But if we try to revoke this from Alice, there we go. We revoked the claim. So now we have deleted this claim. That's basically it. So this is how easy it is. You know, you can see in like, there we go, under 100 lines of code, including comments, we just built a custom palette for our blockchain that allows you to do some very application-specific stuff. And this blockchain can be connected to the Polkadot ecosystem to share the security with all the other blockchains. So this is how we are building the huge ecosystem that is going to be Polkadot. And this is how we're going to connect to the other chains by building functionality that makes it very easy to get started, very easy to get very specific with your logic, and still not deviate from the very practical shortcuts that we've built into Substrate itself, like the metadata sharing, like the forkless upgrades, like the UI compatibility, and so on and so forth. Thank you for listening. If you're interested in this, if you want to check out more content, if you want to check out more tutorials, please go to substrate.dev and go to tutorials there. Including this tutorial, there's a bunch of others there that you can try out, setting up your own private blockchain, building visualizations, stuff like that. Go there, dive in, and I hope you'll have fun, because this is designed to be fun and easy and approachable. And I hope to see you in the Polkadot ecosystem. Thank you very much.
Thank you for the overview, Bruno. It's great to see building your own blockchain can be so simple. For those of you that are just joining us now, if you have any questions during any of the workshops, please feel free to ask them in the chat box. Our speakers will answer them accordingly. Now for our next talk, we actually have a two-part workshop called Terra, a new platform for DeFi DApps with CosmWasm. Ethan Frey, co-founder and CEO at CosmWasm, will guide you through how to build using CosmWasm. William Chen, who leads developer relations at Terra, will teach you how to write smart contracts on Terra. Ethan and William, the stage is all yours.
I am William Chen, Developer Relations at Terra, and today I'm going to be covering smart contracts on Terra and why you might want to consider building your next DApp on Terra's DeFi infrastructure. So Terra is a decentralized stablecoin with global ambition, backed by its sister token Luna, which is the native staked asset of the Terra blockchain. Luna collateralizes the entire Terra economy and provides governance voting rights to its holders. Luna effectively represents a long-term investment in the Terra economy by trading the instability of day-to-day price fluctuations and providing stability to the Terra ecosystem. Luna holders receive a consistent stream of TX fees that only go bigger and stabilize the incentive to hold Luna. So the main topic is why build on Terra. So Terra's smart contract feature is new and nascent and definitely not mature, but I'm going to just go over a couple reasons why you might consider Terra as a potential candidate for your next smart contract. So first of all, I'll have to go into the consensus and block finality of Terra. So Terra is a delegated proof-of-stake consensus chain based on Tendermint BFT as a Cosmos SDK chain. How it works is that the top 100 validators in Luna Stake participate in the block production process. And we're lucky to have a proactive validator community who's actively developing tools such as block explorers and validator notifiers and other tools. Currently, we're at 6 seconds per block with finality, and we have support for potentially hundreds of transactions a second. Terra is a chain that is ready for DeFi applications. So our stablecoin mechanism was built with world e-commerce in mind. So we currently have the Korean won, the US dollar, the Mongolian Turkic, and it's just a marginal cost to add an additional currency to the Terra ecosystem. We have a robust price oracle system that reports on the price of Luna every 30 seconds. And we have fast native on-chain swaps between currencies, between Luna and Terra, and between Terra and Terra currencies. So Terra is really implementing something called money as a protocol, whereby we're creating money that has its own algorithmic and monetary fiscal policy. So this, coupled with the governance feature, enables Terra's economy to act as a sovereign economy driven by its users. The main appeal of Terra, however, comes from the growing, highly active user base with real-world usage. So currently, Luna is third in transaction fees, right after Bitcoin and Ethereum. There are a total of 1.6 million total accounts after 1 year of release, and this number is constantly growing. And we're integrating with real-world apps with actual use cases. So some that come to mind are definitely Chai and MimiChat, which are payment processors that provide discounts to attract users. And Chai in particular is responsible for much of Terra's growth as growing out from Terra. And what's cool about Chai is that it's gotten so big that you can use it at convenience stores, buy groceries with it, integrated in places like We Make Price and Timon, and currently partnered with some of the largest e-commerce retailers in Korea, including Nexon and Kyobo Books. Another interesting use case that Terra has been implicated in is with high yield savings products. So Terra provides this stability feature where for Harubank and Trinito, you can deposit KRT and earn high interest on that KRT compared to a traditional savings account with a bank. So right now, I'm going to spend the rest of the presentation talking about how you can use Terra with the SDKs and how you can start programming things with Terra and eventually use smart contracts. So there are currently 2 Terra SDKs released. One is called Jigu. It's for Python 3. And the other one is called Terra.js, which is for JavaScript. In this workshop, I'll be using the examples with Jigu, but the concepts will be easily translatable into Terra.js with a bit of looking at the documentation. So how Jigu works is that it's a library that enables you to talk with an LCD node. An LCD node is something that a Terra D node runs that exposes its functionality through an HTTP interface. So instead of having to make raw HTTP calls and do serialization and deserialization of the requests and responses, Jigu will handle that all for you and enable you to work within Python as if without realizing that you're working with strings and raw blockchain data. So it allows you to create Pythonic code that works with the Terra blockchain. So once Jigu parses your requests, your request is sent to the LCD and propagated through the rest of the network, and this is how your Python application can interact with the Terra blockchain. So you can get testnet tokens at faucet.terra.money, and this may be useful if you're wanting to follow along with this tutorial. So Jigu does one of two things, and the first thing is querying data. So the blockchain exists out there, and you want to get information about the blockchain into your program. The first thing you want to do is create a Terra object that connects to the LCD. And once you've created that, okay, so here I'm connecting to Soju 14. Soju 14 is the official testnet as of time of recording of the Columbus 3 mainnet. And I'm using the public LCD node at https lcd.terra.dev. And you'll notice that each of the functions are neatly packed into its own submodule within the Soju variable. So I can get the blocks by doing soju.blocks. And there's even an iterator which allows me to iterate through the blocks. I can get the balance for an account by using the bank module. I can get the exchange rate for Luna in USD using the Oracle module. And I can get the market parameters and print them using the market module. So it's really short, and it's really easy to get data from the blockchain by using the functions within each submodule. So the second thing that that the Terra SDK is able to do is to affect change on the blockchain by creating transactions and broadcasting them. So, like before, you're going to connect to an LCD. Here we're going to make a wallet. And a wallet just is an abstraction around a signing key. Here I'm using a random mnemonic key, which gives the wallet signing features. So I'm going to create a message. And a message basically contains all the things I need to interact with the module to change its state. Here I'm using a message send, which is the most basic way of telling the blockchain to move my balance into someone else's balance. So I'm specifying a balance of 23 Luna. Here the unit is ULuna, which is micro units, or 10 to the negative 6. So 23 million micro Luna is 23 Luna. I'm going to specify a fee, and I'm going to send the message. I'm going to sign the message and create a transaction. And then finally, I'm going to broadcast that message. And then you should see a successful transaction. And then you can go into Terra Finder, look up the transaction hash, and you can see the exact transaction being posted from Python. So I just wanted to point to the fact that you can actually put multiple messages in a TX. So you can, okay, here I'm doing two swaps, one from Luna to USD and the another from Luna to KRW. And first I'm going to specify a fee that's higher than the one before because this is going to require more data. And then I'm going to sign the messages and create a transaction and broadcast like before. So this is how you can put multiple messages inside a transaction and broadcast it at the same time. So you can think of messages as transactions in Ethereum because messages kind of are the ones that are actually performing the state changes. So now if you've gotten a bit more comfortable with the SDKs, just exploring around the documentation in exploring each of the different modules and each of their functions, as well as creating different types of transactions such as message delegate, message undelegate, and playing with other things other than message send and message swap. We can progress to the smart contract section. So smart contracts are powered by CosmWasm, which is led by the Confio team, and I'm going to include a video after this where they explain more about the system they've created. But what they've been able to do is create a system where you can execute WASM smart contracts or WebAssembly smart contracts on the Terra blockchain. So what makes WASM or WebAssembly an ideal execution environment for smart contracts is that it is designed to be a portable compilation target with small binaries, small dependencies, and works at a sufficiently low level to be and is designed to be portable and safe, which are all the things that we want in a smart contract execution environment. The other thing is that the way that CosmWasm has designed smart contracts is that they have potential to be multi-chain smart contracts. So in one sense of multi-chain, you can almost like write one contract and then deploy on multiple chains. And in another sense, once IBC rolls out, contracts will be able to call other contracts on other chains through IBC. So currently, we only support Rust for writing smart contracts, but the CosmWasm team has expressed the possibility of porting the libraries that they've created to other things such as AssemblyScript and TinyGo. So the scope of possible languages to cover CosmWasm smart contracts is potentially much larger. But right now, the only language runtime for which mature tooling exists is Rust. So unfortunately, we'll have to use that. But I don't think that it will hinder too many people from using CosmWasm, because the amount of Rust you need to know is actually quite minimal. You just need to be familiar with the simple borrowing, and because smart contract logic isn't supposed to be too complicated. If you can implement your contract with a bunch of read and writes and managing balances, doing a bit of arithmetic, you should be good. So I'm just going to go over the smart contract architecture, or what you need to write in order to write a smart contract. So a smart contract revolves around 3 entry points defined as functions in your Rust code. So the first is the constructor, which sets the initial state of your smart contract, and this is sent in a message instantiate contract. The second one is a handle method, which will implement the different functions of your contract. So, for instance, if I had an ERC20 token, the handle method should be able to receive different requests or different functions through the handle message, and implement things like burn, transfer, approve, etc. And finally, you have to define a querier, which tells the contract how to get data and interpret it back into a form that users can understand. So this is just the workflow of how a contract writer creates a contract on the Terra blockchain. So a contract writer will write his program first in Rust, and then compile it into a WASM binary that he will include in a message store code. Once he has this message store code, he will send it to the blockchain, and the WASM module will sort of store the code on the blockchain. So here, CosmWasm has decided to learn from Ethereum and realize that that they should decouple the storing of a blockchain of a smart contract's code and and the actual instantiation of a contract. For example, there can be many contracts that use the same code, such as one ERC20 token code, being used by multiple ERC20 implementations. So here we see the same code being used in two different contracts by contract creator A and contract creator B, each with their own init message, which customizes the contract. And then the module assigns a different contract address to each contract that has been created, as well as the contract's own private state. So here's an example of how you can use Jigu to upload code to the Terra blockchain using these messages. So as before, what we want to do is create a message, put it in a transaction, sign the transaction, and then broadcast it. It's a very simple process, so I'm just going to walk through. First, you're going to load the contract file and then encode it into base64. Next, you'll create the message like before, and then you'll broadcast the transaction. And at the end, you'll get the code ID, which is in the blockchain events, and that is just the code ID of the code that you uploaded, but no contract has yet been created. Next, we'll go over how to instantiate a contract. So remember that we had saved the code ID from the uploading the contract before. Now we want to instantiate a contract, and then we're getting a contract address back. So here I am creating the message using the code ID I had that was returned to me from the last execution. And you'll realize that the init message that your contract understands is actually a message in JSON that gets automatically parsed by your contract into the right configuration. Here I've decided to name my token William Coin with the symbol WILL. And you can see that you can also put an initial amount of coins to fund the contract. So I'll just broadcast the transaction and get the contract address. And this should create my contract. So now my contract will exist at a normal Terra address. So this is just simplified flow of how a contract gets executed. So the contract user will define the function that he wants to call on the contract, such as transfer or burn, and put that in a message called a message execute contract. And then he'll sign and broadcast the message execute contract, which will get handled by the WASM module, and load the contract code with the handle message, specifying the arguments to pass to the contract's handle function. Next, the contract will be able to access the state and commit more state. And finally, when the contract when the contract finishes execution, the contract can affect the rest of the blockchain by emitting its own messages like message swap, message send, and message delegate. So here's an example of executing a contract. So we'll create a message, and we'll use the contract address that we got. And you'll notice that the message or the handle message is JSON. So here we're trying to use the transfer method of the contract with 5,000 as the amount and a random account as the recipient. And there is also an ability to add coins to the contract with your contract call, which will be required for some contracts, such as like a vending machine type contract where you have to deposit some Luna to effect an execution. And the contract can actually pull which types of coins have been sent to it and see if the fee paid is enough. So we'll just broadcast the transaction, and that should execute the contract. So it's that simple. So finally, how do we get data actually out of the contract? So since for my last example, I transferred some coins from one account to another, the one thing I want to be interested in is perhaps the balance. So I need to create something called the query message that the query function on the contract will understand. So the query message is JSON, like the init message and handle message. And there's no transaction needed. Just query the WASM module. And the output is JSON. So as you can see, the Terra integration for smart contracts is very simple and just adds 3 messages and a querying mechanism to the Terra blockchain. But this allows users to commit arbitrary code to the blockchain and finally allows third-party developers to add their own logic rather than depend on Terra's native modules. So I'm just going to talk about the developer tools that we're working on that we'll be seeing in the next couple months. So the first is Local Terra. Local Terra is a one-click blockchain and ecosystem tool for Terra. So what it does is it spins up an LCD node, which is a Terra node REST API server. It spins up FCD, which is a block indexer, which is the backbone for Station, which is a wallet, and Finder, which is a blockchain explorer. And it gives you a way to quickly control and inspect the world state, which makes it easy to speed up smart contract development and testing. Next, we're going to create an easy way to set up the general boilerplate for writing a DApp front end. So we want to make it as easy as creating a new React app with yarn create Terra DApp, and this is going to allow people to quickly get set up with a usable front end to use with their smart contract. This will lower the barrier to entry by getting you set up quickly with Terra blockchain. And finally, we're planning to release a Chrome extension version of Station, which will bring the MetaMask or MyEther wallet experience to Terra and allow you to allow users to directly interact with smart contracts from within a website. So that mainly covers how you can get started with smart contracts, and you can get started today with the smart contract documentation on the Terra official documentation available at docs.terra.money. Right now, I'm going to pass it over to Ethan Frey of CosmWasm, and he's going to explain more about the mechanism that allows Terra to run smart contracts. Thank you.
Hello, my name is Ethan Frey, and I'm the co-founder and CEO of CosmWasm. Today I'll explain what CosmWasm is and why it might be interesting to you in your project. First of all, what is CosmWasm? CosmWasm is a multi-chain smart contracting solution. That means we're not a blockchain. Rather, we are a module that can be embedded in many different blockchains and is currently many different blockchains. That is a very powerful point. I'll break it down in a few ways. What it means currently is if you are a developer, you can write contracts that run not just on one chain, but on many different chains and leverage the same contract and same knowledge many places. As a blockchain and you want to add smart contracting capabilities, you can embed CosmWasm into your blockchain. And that allows you to access existing contracts in dev community from many different blockchains. So we don't have to lock each one and learn a new language for each blockchain. We can have one that is generally extensible. We also have deep Cosmos SDK integration. Currently, the only platform that we are integrated with is Cosmos SDK. We would like to extend that in the future once we hit more stability, like our 1.0 release. But that allows, there are dozens of different projects currently building on the Cosmos SDK. Most of them have lots of different modules written in native code, Go code, to add custom functionality. And this allows us to have contracts that don't just run side by side, but actually call into those native contracts, this native code, and allow the native code to call into the contracts. So we allow deep integration into the runtime. That can be customized for every different blockchain. we have a security first design. When designing CosmWasm, we didn't start with what's the easiest way of making something, let's copy Solidity. We said, how do you make a secure platform? Typically we see Solidity is really easy to get started writing a contract, but pretty hard to write a secure one. And there's a huge rage for bugs in there and audits and a huge community there. And that seemed very dangerous. So we said, we can raise the bar for writing a contract, make it a little harder to write a basic contract, but lower the difficulty of writing a secure contract. And this space here is a space of actually functional but insecure contracts. So we're trying to lose that space and say there's not much space for that. There are some issues which you can document, but we try to limit the number of issues that you can bite you when designing smart contracts. And we are now refining the user experience to make it easier and easier to write contracts on that system. We are based on the WebAssembly virtual machine. We do not write our own virtual machine. We are using WebAssembly. WebAssembly is available in all browsers, but also there are quite a few native runtime solutions that run it. One is Wasmer, but there's Wasm Time and CraneLift, and there are quite a few other out there that run as binaries on multi-platform systems. We are using that virtual machine. It's a well-defined virtual machine. There are many implementations that run code from that virtual machine and optimize it, the compilers. And there are many different mature languages that compile down to it. So we don't need to reinvent the wheel. We can choose one of the virtual machine implementations to use, and we can choose various languages that compile down to it. We currently focus on Rust, and we're looking at more. There are probably 6 to 8 languages that compile well to WebAssembly, and another dozen or so that are working on that support. And we're currently live on testnets from 5 projects. So this is not a theoretical idea. This actually does have users. The history of CosmWasm. Where did this come from? So first of all, my name is Frey. I was a third developer at Cosmos. If you've heard of them, they're probably top 20 chain now somewhere. And I got inspired by them with a Tendermint. I started working on Tendermint and then got involved with them. I came in there because I'd been working a lot of back-end web design and wanted to get into blockchain. I was frustrated with the tooling on Ethereum, for example, on Solidity 16, and wanted to say, I want to have secure development. I want to have easy development on blockchains, and it was amazing what they were offering with Tendermint. You just worry about the app logic and not all of the rest of the blockchain. And it was written in Go, which is a language I knew and had good tooling. So I built the first Cosmos SDK in 2017. I worked on the IBC white paper then, and I'm really committed to the Cosmos ecosystem. So I've left Cosmos and worked on other projects around them, building on the same technology. And at the Cosmos Hackathon in Berlin, 2019, we had a nice, cool team. So we ended up with Aaron from Regen Network, Jehan from Altea, Shane from True Story, and Pedro from Wallet Connect. And we all sat around like 5 leads of projects. We just made a little team. We said, let's build something. And ideas went out there. And one of the ideas that just stuck, we were sitting around there. It was just starting Saturday, and Friday evening, we're sitting around the table drinking and chatting ideas, and it came out, let's build a smart contracting engine. WebAssembly. There's tooling around it now. Everyone's doing this thing. Can we build a WebAssembly smart contracting platform and integrate it into SDK in 2 days? And, well, the later at night it got, the cooler the idea seemed, because, well, it seemed like a stretch goal, but an awesome project. So we tried it, and we basically banged out code for 2 days, very little sleep. I'm very, very thankful to Jehan, who was a Rust expert. I was just learning it while coding. And I brought a lot of the Go code in there. So we were working on the Go side, Rust side, we integrated, learned from each other, and got a working prototype in 2 days. And Pedro threw a UI in it so you could actually view the contracts. So that's pretty amazing stuff to get done in 2 days. So we got it, we presented it, people were impressed, and we got a grant to follow up from the Unitize Foundation. And I worked part-time on that alone, basically, from September 2019 to January 2020, and got a 0.6 release, which was basically stable. It was usable. It had gas metering. You had the basic functionality to write contracts. It didn't have deep native integration, but you can move tokens around. And it was actually pretty cool, and people started using it. I got docs out there, people started building on this. They're very interested. And since then, we've built out, we got another grant, and we've gotten some contracts and built up partnerships with people that are building on it to get to the 5 different projects building on it actively, and many more interested. So we have a small team now. We have 5 people working on this to bring it to really production ready. And we've added quite a lot of features that people have requested. And we run currently on a few incentivized testnets, and this is getting very, very close to mainnet ready. So we are currently planning a 1.0 release around August. This will be stable, forwards compatible. We provide, if you write contracts on 1.0, we will provide upgrades for the module. We will allow those 1.0 contracts to run on a 2.0 chain, etc. So this is really something that can run a mainnet. We have an audit at one point, bug bounties on it, and we'll start building out developer tooling around it because we have a stable framework to build on. Currently we support Rust, and both the runtime and contracts are written in Rust. And we are working currently on prototyping Go via TinyGo and assembly script contracting languages. And they're waiting on the stable APIs. And we have some first experiments on them. We're also working on a front-end framework to build DApps that wraps it called CosmJS, which is similar to Web3 in goals. It's different design, but similar goals. You can quickly add a JavaScript front-end that will talk to your CosmWasm contracts. And on that, we can start building better dev UX tools, deploy tools, debug tools, analytics tools, because we have a stable API. And it guarantees that there's a clear path to port it in the future. Your 1.0 code should work on 1.1 and 1.2, and we should have a clear path to port it to 2.0. So this is the point we can really start building a large community of people building lots of tooling around us. So we're really excited to get more people using it, and it's really going from early adopters to, from pioneers and early adopters. So it's usable now. Not just on experimentation, but really going to be usable for building production software. And we look forward to building custom solutions, helping people build contracts and integrating with their custom chains. So really, we have the capacity to help people build the solutions they need. So we are looking to onboard more developers and more projects onto the system, principally. So if you want to have CosmWasm on your chain, talk to us. And if you want to learn how to CosmWasm contracts and run your contracts on lots of different chains, great time to learn it. After that, our next stop is IBC support. IBC is inter-blockchain communication. It's Cosmos' flagship design. It was written in the 2016 white paper, way ahead of its time. I worked on refining a very clear technical spec in 2017. Chris Goes has gone in 2019 a very, very much more extensible spec. It's basically TCP/IP of blockchains. It allows this SSL on top, TSL, and everything on there. It allows super secure ways of proving with light clients on both sides. You can send packets between blockchains. It's asynchronous message passing with receipts, guarantee delivery in order, timeouts, all of it on the protocol level guaranteed. And you can start building distributed systems on top of that. So you can make API calls between blockchains. Your contract writes something and you guarantee it will read it or get an error message passed back within certain bounds. So that allows you not to trust an oracle or a special privileged relayer, but really it's really powerful. So you can start building multi-chain solutions that you can have contract in chain A and chain B communicating with each other. So you can have your DAO over this chain controlling, sending money here and controlling your assets in a DEX on another chain. You can move your tokens over here, you can trade them, you can stake them for staking derivatives, you can send them back over here as you want, and that all can be controlled by logic on multiple chains. This is coming out in Cosmos Stargate, should be later this year, and we will have a 2.0 release built on Stargate that supports that. And that we will allow not just the chains and the native code, but smart contracts to send messages to contracts on any other chain. Currently only supports Cosmos SDK. Many other BFT consensus engines with proof of finality can be adapted to support light clients and IBC. That includes Polkadot's Grandpa, Avalanche from Ava Labs, and Nia Protocols. Those are all are theoretically compatible with IBC because they provide instant finality, and they can provably say this block is in the chain or not, rather than probabilistic proof of work finality. So this allows a truly multi-chain solution. Once that's implemented, not only will you be able to run the same contract on multiple different chains, but these contracts will be able to run over the chains. So you can have some options contract running on the DEX chain, which actually has native code to run a DEX, really high quality, and you can have a DAO chain that has maybe things here, and maybe you have a ZK snark chain that has a bunch of primitives for running zero-knowledge proofs. And you can pass it over to the mixnet, and you can actually customize stuff, and these contracts not just you as an external user, these contracts can then move stuff around there and control that with their own logic on-chain. That, I think, opens a huge door to design, and by allowing not just native code, but smart contracts to do that on both sides, smart contracts that communicate on both sides, we allow a huge space for rapid development in this area, which I think is really the new frontier of blockchain interoperability. So we look forward to seeing that end of this year, early next year, and we are waiting for Cosmos Stargate to finish, and we are following their development with our IBC development. So I think this could be a really huge shift. So if you get in now on CosmWasm, building your contracts that run on many chains, in half a year or so, you'll be able to have those contracts actually talk to multiple chains, one contract. So I'm switching gears now. Now that you're so if you're a techie, this is where it's focusing tech heavy. If you just wondered what it is and how it's used for your project, well, we covered that. So digging into the tech here, how does CosmWasm work? We use Wasm.io to run the bytecode. It's a Rust project. It's pretty solid thing. There are a lot of other people running it in your protocol, for example. And we precompile, what does it precompiles WebAssembly to sandboxed native code. It has different backends. We're using single pass, which is a very quick compiler, has no real attack surface, and it makes a bit slower code. It runs about 20 times slower than native Rust code. You could use an LLVM compiler. It takes that WASM, compiles a really, really optimized native code, and actually runs about half the speed of native Rust code. So your WASM can basically run more or less native code and full crypto on it. The problem with that one is it takes a while to compile, so the compiling step could be an attack surface. So we're looking at doing some, permissioned control of uploading it permissionless with single pass. And if you need the extra performance boost, we can have a permission step that has some people validate it's okay before compiling it down to LLVM, because otherwise you can kind of slow down the blockchain considerably by running bad or malicious WASM that can just slow down the compiler a lot. But yeah, so it does that, has lots of different functionality here, and it runs native code that's completely sandboxed. There's no access to syscalls. It is metered with gas, injects gas metering involved in it, and all CPU usage is metered, and is isolated memory space. It records its own memory, it has metered CPU usage, and it can touch nothing in the system. The only thing it can touch is imports. We provide some imports there, and we can then write defensive code to guarantee these imports are safe. That's our virtual machine layer, which wraps around Wasmer. So we have CosmWasm VM, which wraps around Wasmer, that provides our custom imports. We provide read and write access to a subset of blockchain space. We provide like a subkey under a prefix under the blockchain Merkle tree, and in that prefix it can read and write and nothing else. And we can limit how much it can read and write to that space. It can query other modules, read only in a very specific API to other native modules and contracts. And we can add more blockchain specific APIs, which are also called precompiles. This will call out into the blockchain itself to do some stateless logic. Currently we have address formatting because we support multiple chains. They're different native address formats. So we can't compile that in the blockchain. We have to say, well, convert a string address to a binary address is blockchain specific. So we call out to the blockchain itself to do that. We could add things like, signature verification, like Ethereum does, precompiles. Other stuff could go in there. And we can meter everything with gas. We allow no network access, no non-determinism, and no jailbreaking. We also disallow any float operations, which are theoretically non-deterministic. There's no random access here, obviously, because there's no syscalls, and we don't provide it. So we basically guarantee you cannot break consensus state. They will act deterministically. We don't allow multi-threaded. There are few WASM arguments. We go through all the WASM opcode, and if they use anything that's not in our safe set of WASM, we reject the contract on upload. Memory versus storage. So while we have this, we make the difference explicit. In Solidity, they mix them together. Instance variables and state storage are transparent to the user, which can be nice for development, but it's hard to reason about. In our model, the code has fast access to RAM, native speed. it has almost unlimited RAM. You can allocate currently, unless you set another limit yourself, you can allocate 4 gigabytes of RAM in your contract. You can explicitly set that less, 32 megabytes or 5 megabytes. But you can get up to that much. You can't actually use that much because CPU limits. You cannot write 4 billion zeros in space in a CPU gas limit, but you can allocate as much as you need. So any memory you can write to, it just will give you that memory access. So great, memory is cheap. CPU costs and writing storage and reading is very expensive. The price there is much, much higher. So we want to make that very explicit. You have to explicitly read and write to the database. So we have a simple interface that allows you to read and write typed data from the database. Great, but you have to explicitly do it. I think it's a critical difference from Solidity. Also, security first. We define security. So we looked over the list of, Open Zeppelin exposes the top 15, 20 security holes, exploits that are known in Ethereum. And we went through that and made sure that we could patch all we could. Reentrancy is impossible to design. We did use an actor model. I'll get to soon. Overflows and underflows, Rust will panic if you do that. We said it that way. Unexpected ether is a bad design pattern. You can have trivial bugs because we can send tokens to the contract. Delegate call, we don't allow it. We have another way of doing those proxies of migrating code. Default visibilities, you have to explicitly set them. So we went through this whole list basically and closed all we could by design. In particular, we used the actor model for dispatching messages. This negates all possible reentrancy attacks. So rather than your contract A calling to contract B, and then contract B calling to contract A, and contract A is not persisted all their data in state, some in memory and some in database, and that gets all kinds of little subtle flaws in Ethereum, kind of like limit the gas this has, so it can't really call back into your contract. This is really bug prone. What we do simply is use the actor model. That means actor model, you get a message and you return messages. So your contract will process it and return the message. So if I want to call that, when I say basically I do my work, I save my work, and I return a message that we execute on other contract. That means I do not get a result from it, but it means I am done if saved my work before it starts. All you get to know about is whether it errored or not. We run all the messages you dispatch in the same transaction. If any of those contracts fail, then it will revert the entire transaction. All state changes get reverted. So I can basically say, if an escrow happens, I will optimistically update the escrow got sent, I delete the escrow, and return a message to move the money. If that succeeds, great. If it fails, then it reverts the whole transaction and act like nothing ever happened. My delete escrow command is also deleted. That is usually the error handling you want. It's only one you have here. You can do complex logic to try to get other use cases there. It is kind of possible. Returning messages back is possible. It's not, it's a little trickier, and we'll demonstrate that, but basically the standard use case of just assume it works, and if it errors, roll back everything is the only one you get by default, unless you really try to do something else. There's no reentrancy possibility. And you don't forget to check the return value of a send. It might return a 0 or false if it didn't work. Don't worry about it. It just always checks that. Like I said, we have built-in overflow checks. We have an explicit API for query and handle methods. So you have to explicitly add those methods that you want to be exposed. They don't just happen to be exposed. And yeah, everything's very explicit there. You have to call into stuff and make sure that there's no loops possible. And we use the Rust language. We ensure the Rust language has a lot of functionality to ensure contract safety. That means we take advantage of, they have a lot of control of type safety, of memory usage, of mutability issues, and so often you compile code and it yells at you 3 times the compiler, and you realize, hey, these are subtle bugs that I forgot to handle. I didn't handle this error case here. And so the compiler will give you warnings or errors on many, many possible cases, and by utilizing that, you can avoid large costs of bugs because the compiler checks your logic quite a bit, whereas our framework doesn't allow these larger design issues to happen. Rust also provides first-class test tooling. They have quick check, they have fuzzing. You can do very, very complex testing with Rust as unit tests on the Rust code before you compile to WASM, which allows you to get very, very high levels of reliability and security on your code. You don't have to upload code to a virtual machine and run it. You can actually run it as Rust, natively link stuff, and then when you've tested that heavily in unit tests, you then compile it and run high-level integration tests on it, seeing how it works in reality with a real thing. But you can get much lower ones, give you full stack trace exactly what failed, and it's really, really nice compared to trying to debug Solidity, for example. So yeah, contracts and native code is love. We are not trying to make a general purpose smart contracting platform. There are many other ones that are doing that very well. For example, Nia Protocol is just allowing you to write smart contracts on their platform. And they do an amazing job doing that. Also using WASM and also using WASMer background. However, it's just contracts. And for some people, that's amazing. Many other platforms, however, are currently building out native code. They are building a blockchain with custom native functionality that may need privileged access to various things. You might need privileged things you don't want exposed to generic contracts, right? They control the value set with their staking algorithms. They want to have very optimized cryptography using native code. They want to have that native code. So we allow the integration between contracts and native code. And I think that's what really differentiates us from many other projects, which are awesome projects, but we are going for a different route. We are basically not generic smart contracting platform. We are one that ties deeply to native code. So you can currently call into the bank, which is coin transfers and staking modules in Cosmos SDK and other contracts, but you can easily extend that. So for example, on Terra, they wrote a swap, more of a trading swap DEX thing, and an Oracle modules for exchange rates in Go native code. And they wanted to add smart contracting capability on top of it. So we allow that. We worked with them to add extensibility. They can now expose an API, so and don't have to recompile a Rust code or anything. They expose it in their blockchain, the API they want to expose, and it's passed down into our contracts. A generic contract can run on their platform with no modifications, and a contract can import a crate to add their extra custom types, and it will then mark a feature flag that needs Terra. And that contract then has access to their swap and Oracle module, certain queries and messages. And it can call into the native code very nicely, transparently, just as easy as it calls into the staking module. However, that module is then flagged with a Terra flag, which means if you try to upload that Terra specific contract to another blockchain like Enigma, it will reject it because it requires the Oracle and swap contracts. So we allow you to flexibly do this. So you can have very generic contracts that rely on none of these extra pieces, which can run on any code. And you can have custom contracts that are really chain specific, that make use of all the native APIs of one chain and only chain specific. But all that learnings you've had for tooling, for dev environment is the same setup you have. You just have a new API call extended for this chain. So we allow these contracts to run on one chain or multiple chains. And the more you customize it, it's great. But all that knowledge you have, all of that learning you have as developers can be ported to the other chain. So if you learn how to write Terra-specific contracts, that's wonderful. And now if you want to write contracts for another chain, just if you don't use the swap and Oracle modules, that contract works everywhere else. You can write your ERC20 modules, you can write NFTs, you can write your other stuff out there, all you want, your DAOs, as long as you're not relying on those modules. The same tooling you've learned will work anywhere. So it's a really opt-in to native code. And now I hope you've enjoyed this. And I'd love you if you're interested in CosmWasm, if you think it's cool for your project, if you want to embed it into your blockchain, if you want to start developing on it, that's wonderful. You can learn more about us, CosmWasm.com. Also links to our documentation and gives you a little overview. And links to our Twitter account and our Medium account and various other things. Find us on Twitter. Please follow us there for latest news. On GitHub, you can find CosmWasm. CosmWasm is our main entry point, and we have a number of other repos as well. And on Vimeo, you can look for CosmWasm to find a list of our community calls. We have a bi-weekly community calls, which are recorded, and you can see what our updates. So we get a half hour to an hour discussion of our current updates and roadmaps, if you like to watch videos and follow our current progress. It's a very nice way of keeping an eye on it every 2 weeks. And finally, we will be involved at the hackathon. So we are working with Terra on the hackathon in the next few days. So please join that. I'll be doing a workshop on that one. And there's a lot of resources that Terra has also assembled on how to onboard. So come, please join that, write your first contracts, learn how to use the Terra DEX with smart contracts, and write CosmWasm smart contracts in general. We've read a lot of stuff. So I'd be very happy to see you there and get your hands dirty as developers using it. If you are wanting to, you can also join a Telegram channel. We have Discord channels. It's all linked from our website. If you are a zone that is interested in building it, reach out to me. My name is Ethan at confio.tech or ethan@cosmwasm.com. You can reach out to me, and I'm also curious, after 1.0, we're curious about integrating with other blockchains besides the 5 or 6 we are currently working on. Thank you very much for your time. I hope you enjoyed this talk, and look forward to seeing
Thank you, William and Ethan, for the deep dive. It was great having you. For those of you that are just joining us now, if you have any questions during the talks, please feel free to ask them in chat. Our speakers will answer them accordingly. For our next talk, Connor McEwen, who is the mobile team lead at Celo, and Josh Kreitz, partner and product lead at Celo, will be giving a workshop called A Global Mobile Blockchain, How Celo Works. This will be a deep dive into the Celo platform and their newly released wallet, Valora. Connor and Josh, the stage is all yours.
So I'll start with kind of our onboarding flow. Now, I'm not sure if anyone else remembers this, but I remember when I first started using Venmo and got invited to it, I was actively recruiting my friends to start using it. I would send them some money and say, hey, when we're at dinner and, you know, I'm not going to put my credit card down, I'm going to send you $20 on this app and you got to install it because it'll make your life way better. Unfortunately, with existing cryptocurrencies, there's no real way to do that, right? Because you can't send someone money without knowing their address. What's great about our lightweight identity protocol is that it solves that problem, and I'll tell you how right here. So if you're inviting someone to the Celo network, what you'll first do is generate a new private key and transfer a little bit of money on it. This money is enough to verify, and so then you'll text that private key to whichever person you're trying to invite to the network. So that person will take the small amount of money on the invitation private key. They'll generate a new private key in their app, transfer that money, and then use that small amount of money to pay for verification. So then they have a new verified account. And the last piece is that when you initially wanted to send someone money, you can actually escrow a larger sum of money with their phone number and that private key that you sent. So only after verifying their phone number are they able to withdraw money. So if I wanted to pay you back $20 for dinner, I'd transfer a little bit to that private key. I would escrow the rest of the $20, and then only after verifying would you have access to that $20. We think this is a much more secure experience than sending private keys around, but also provides really great usability and the ability to invite new users to the network. As I mentioned before, if you're curious, we'd love for you to take a look at our escrow contracts so you can understand a little bit more about how it works. There are a few other features that I love to talk about too in Velora. One of them is key storage. So we believe that while it should be non-custodial, there should be no central entity that holds a user's funds unless they want to. And so we designed Velora such that users are the only people who have access to their private key and funds. This is important thing to worry about, though, right? Because obviously we want people to keep their key safe, and we don't want anyone to be able to take a user's money. And so what we've done is encrypt the private key using both a client-side generated pepper that's random as well as a PIN. So that even if someone is able to get a file system access to the mobile wallet, they will not be able to unlock the phone to send funds anywhere. We also have spent a while trying to make sure that we educate users about how to custody their account key, as we call our backup phrase that you might have heard as well, because that's really important in order to be able to keep access to your funds in case you lose your phone or anything like that. Another feature that we built because of our experiences out in the field is Data Saver. So even though we have made the light client as light as possible in terms of syncing block headers, in some cases the latency and the network conditions are just so bad that it's impossible for a user to use a light node. In that case, we enable people to still keep their keys on their device, but use a hosted full node in order to communicate with the network. This, we found, gives people who otherwise wouldn't be able to access the system the ability to access it. And then the last piece, as I mentioned, is you might have heard me talk about CP Dodo and the stability protocol. Well, we make it really easy for Velora users to exchange between Celo dollars and Celo to participate in the stability protocol in the app. And that's, again, using that contract kit that I mentioned before to make it really simple to interact with the contracts. A couple lessons learned from spending some time building this mobile wallet. I think the first one is, as I mentioned, full stack is really hard. Many layers means that there's many places for errors. And especially in the early days when we were developing the protocol quickly, it was difficult to keep a stable environment, to keep up with changes, and to make sure that we could deliver that wallet experience that we wanted to. However, I think that trade-off, as I mentioned, is really worth it because we can develop a product experience that's truly compelling. There's no, we're dependent on this thing that we don't control, or we have to wait for longer blocks, or, it just gives us the ability to iterate quickly and to kind of work on a product experience we're proud of. The second piece is that good async handling is your friend. As I'm sure folks who have developed a blockchain before, things might take a little bit longer than you're used to, and it's really important to have good asynchronous handling. Since we use React Native and TypeScript, we're able to use a library called Redux Saga, and that really helped us with control flow, being able to block different things on network status or sync status, but still have a simple developer experience. And then the last piece, as I mentioned, is that user research is really key. Even though we had some ideas about how we wanted to build things and what we wanted to build, we need to test our assumptions with real people in order to understand what was true and what wasn't. I think that there's no way we would have built the product experience that we ended up with today had we not spent time understanding the needs of people around the world. So hopefully that was a good bit of information about what we've already built. But I'd love to turn it over to Josh to talk about, as a developer, what you can build.
All right, thanks a lot, Connor. So to make it easier for DApp developers, we created the mobile first SDK. And this is really what we used internally to build the Valora app. The two pieces being the contract kit that Connor mentioned, as well as the DApp kit. The DApp kit's a little bit more for advanced usage, but I'll get into that in a minute. So we designed the Celo SDK from the ground up to make it easy to build mobile first apps. Connor, can you just go back one slide? And the Celo SDK offers several advantages over similar blockchain development tools because Celo has several more primitives available that Connor mentioned. So Connor mentioned the exchange, and we have easy integration with Celo assets, being the Celo native asset and the Celo dollar. The contract kit comes with core contract wrappers that are already initialized, so you don't have to initialize a set of contracts every time you set up your application. And we have easy access to the lightweight identity layer that Connor mentioned that maps phone numbers to addresses. And also easily paying transaction fees in alternative currencies. So you don't have to use the Celo native asset to pay transaction fees. You can use alternative currencies, and this is easy to implement using the SDK. So as we add new currencies that are approved for paying transaction fees, this will be easy to integrate into your application. So you can go to the next slide, Connor. So currently the Celo SDK has two parts, the contract kit and the DApp kit. And the contract kit works at a little bit lower layer. It's like a wrapper around the Celo core contracts. So it makes it easy to access things like the stability mechanism, the validator sets, the oracles that are helping with the stability mechanism, and accessing the identity layer. You can import contract kit into your project and have quick access to the core contracts without having to initialize any of these contracts. You can just access them. They're right in the JavaScript objects. And DAppKit is more like an interface between applications that are built on top of the Celo protocol. So it's kind of at the top layer. It's currently designed to interface with the Valora wallet, and the Valora wallet is acting like the user's connection to the underlying Celo protocol. So reading and writing to Celo can be managed by Valora using the DAppKit, so you don't have to manage connections, user accounts, or signing transactions yourself. You can just use the DAppKit for this. So, as I mentioned, Contract Kit wraps the Celo core contracts, including the core ERC20 contracts, in an easy-to-use interface. So, as Connor mentioned, Celo includes the EVM as the execution engine, so our core token contracts follow the ERC20 standard. And Contract Kit is currently written in TypeScript, so it easily integrates with any JavaScript or TypeScript project, and we're hoping to support more languages soon. And we welcome any contributions from the community to either Contract Kit or DAppKit. As Connor mentioned, this is a fully open source project, so as you guys start playing with this, we'd like to hear what you are interested in adding, and would like to help you add it as well. So DAppKit relies on the Contract Kit for much of its functionality. DAppKit makes it easy to access some of the core features of Celo, such as the stable value currencies in a user's Valora wallet. It makes it easy to specify which currency a user should pay transaction fees in, and to look up Celo verified phone numbers and accounts in a specific user's contact list. So this makes for a very different user experience than what you might be used to developing on other blockchains. We built DAppKit in TypeScript as well, and we've created example apps written in Expo. So anybody with web development experience can jump in. You don't need too much mobile development experience to get started. But the DAppKit will be comfortable for mobile developers that are familiar with React Native, and Expo makes mobile development with React Native similar to a more traditional web development experience. But it does take some resourcefulness and getting used to if this is a new framework for you. So yeah, if you haven't heard of Expo yet, it's super easy to get started with. And as you get started building on DAppKit, you'll get really familiar with Expo and React Native as well. All right. Yeah, so this is a short demo. Of the DAppKit in action. This is our example Dapp. So you can see on the main page we ask users to log in. There's a few buttons. It defers to the wallet for the user to log in, and the wallet asks the user if they should sign in. And once they're signed in, you can see their account, their phone number, and their balance. It's reading a smart contract, and it just popped up. It's a little small there, but it popped up and it just says hello with a couple wave emojis. That's the name of this Hello World contract. And now we're going to ask the wallet to update the name of the contract. So this is deferring to the wallet to actually sign a transaction and send it to the network. And we're just updating it to Hello SF Blockchain Week. And we can see that the transaction already executed on the testnet, and we read the contract name again, and it's updated to Hello SF Blockchain Week. So that was a pretty quick run through of the example, but you can download and explore this example, look at the code, and modify it yourself. It's a good boilerplate for starting your own project and just playing around with DAppKit and ContractKit and getting started on the AlphaHorizon test network. But here's an example of a Dapp that we built using DAppKit with a similar boilerplate as the previous example we just showed. This is a saving circle Dapp. A saving circle is a strategy to help a group of people save money, where they can contribute and withdraw funds at different times. So here we're showing someone withdrawing the group's savings after it was built up. So you can see that a call is initiated to the smart contract. We have to sign the transaction in the wallet and pay for gas. Luckily, we can pay for gas in Celo dollars. And then we just have to approve the transaction in the Celo wallet. So once the user approves the transaction, the funds from the savings circle are deposited directly into the user's wallet, and then the screen will switch back to the Dapp. So we're just deferring to the wallet for some actions based on the preference of the developer of the application. So the application developers don't have to worry about managing the accounts, the keys, or these transfers. It's just handled by DAppKit, making it really easy. So yeah, going on to some of the other projects that we've seen built on Celo in the past couple months. In some hackathons and incubators, we've seen Impact Market working on a universal basic income game. That's pretty cool to see. We've seen Bienvenir helping refugees get financial support when they move to new countries and they don't have access to existing financial or banking infrastructure, and they need access. PesaBase is building an integration with M-Pesa, which is a huge payments network in Africa. So helping people in Africa get access to financial services, as is DunyaPay. They're helping with low-cost money transfers in sub-Saharan Africa, and also Multiply Charity, which is increasing transparency and impact of donations with alternative currencies. Currently working on Ethereum and Celo. So yeah, going on to what will you guys build? Just from my perspective, with teams I've been working with, looking at other blockchains and kind of the way things have been going in the space, I'm really excited to see decentralized financial applications built on Celo. Ethereum has seen a lot of activity in the decentralized finance space, and what is possible on Ethereum is also possible on Celo. As Connor mentioned, Celo is still really new. We haven't seen a lot of development here, so it's a green pasture. There's a lot of potential here, and I'm excited to see what happens, particularly things around allowing users to use Celo assets as collateral for loans, or users being able to earn interest by providing loans to other users in the Celo ecosystem. I'm really excited to see bridges to other blockchains. We've seen stablecoins really explode on Ethereum over the past few months. And Celo has a unique solution to the stablecoin problem. There's the problem between decentralization and centralization and how those assets are collateralized. Celo is kind of unique in this domain. So how does the Celo dollar fit into this decentralized finance space? This is to be determined. And I think, again, there's like a lot of potential here in terms of what's possible. And I think developers are going to be pivotal in deciding which direction this goes. I'm excited to see advanced user wallets. So as Connor mentioned, Celo is focused on user experience from the beginning, but there's still a lot more work to be done to make these systems even more usable. And I think keyless wallets or smart contract wallets are an underexplored area of research and development. And yeah, I'm excited to see what people come up with. Also, DApps that leverage lightweight identity in new ways. This is a new primitive kind of in the blockchain space. I don't know of another project that has a robust lightweight identity layer. Valora is using it to look up friends and send them money. And this is an obvious first use case for a phone number-based identity system, but there's a lot of potential here. It's, again, an underexplored area of research and development. And I think it's easy to imagine a future where the lightweight identity layer becomes essential beyond just sending payments to build more robust digital identities. And it's interesting to start thinking about what digital identities might look like with advanced user wallets. So yeah, I invite you guys to help us explore these avenues and like see what we can build, because there is a lot of potential here. So yeah, I've got one more slide just inviting you guys to connect in a couple different ways. Celo.org/developers is a great site. Celo.org generally has a ton of great information. You can sign up for our newsletter there in the middle, and then also on Twitter we're at CeloDevs and also at Celo.org. So yeah, I think that's it, and thank you for your time. This has been great, and as Connor said, we'll be around for question and answers, and come visit our virtual booth.
Yeah, we'll be doing a little bit of beta testing of Valora in the virtual booth, so really hope that y'all stop by and we'll chat some more then.
It started simple. A token, a symbol of hard work, of skills, for trust between people. Money was meant to be exchanged for things created and services provided. It takes many forms, both plain and shiny, honoring leaders of the past and those leading us into the future. Somewhere we lost our way. People waged wars over it, big and small, concerned more with growing interest on $244 trillion in debt than growing communities. And many people are left out, 1.7 billion invisible, left behind and underserved. But what if money were more accessible to everyone? A universal symbol for essential needs, for empowerment and connection. People, communities, entire countries prospering. What if money were all of this? What if money were beautiful?
Computer science and the progress that has happened in the last century has given us this huge computational surplus and a great set of protocols and capabilities for creating this security in a new and more comprehensive way in cyberspace.
Truth, on the other hand, is sort of taking matters into your own hand, right? With truth, it's all about interacting with the world directly.
Markets are about story. Great bubbles happen around stories that are really appealing, but also around stories that really do change the world. Right? The internet bubble in the 1990s got way, way ahead of itself, but the internet really changed about everything we did in the world. And so we had the same thing with crypto.
Started simple. A token, a symbol of hard work, of skills, for trust between people. Money was meant to be exchanged for things created and services provided. It takes many forms, both plain and shiny, honoring leaders of the past and those leading us into the future. Somewhere we lost our way. People waged wars over it, big and small, concerned more with growing interest on $244 trillion in debt than growing communities. And many people are left out, 1.7 billion invisible, left behind and underserved. But what if money were more accessible to everyone? A universal symbol for essential needs, for empowerment and connection. People, communities, entire countries prospering. What if money were all of this? What if money were beautiful?
Hi, everyone. Thanks for joining. Excited to be here today. I'm going to talk to you a little bit about Celo, which is a global mobile blockchain. I'm Connor McEwen. So I work for cLabs, which is a company that works on Celo. And kind of my focus is really around mobile and financial experiences. I lead our applications engineering team. And I joined cLabs a little over 2 years ago just to really focus on building out the wallet and the applications engineering team. I'm joined here by my wonderful colleague, Josh.
Hi everyone, glad to be here. I'm doing developer relations with cLabs, so I'm really focused on helping developers build on the Celo protocol.
Awesome, and both Josh and I will be around to answer questions, so if at any point during the presentation you want to pop some questions up, we'll try and stick around to answer them. So first, we're going to tell you a little bit more about Celo. We're going to tell you about how we designed the Celo protocol specifically for mobile. We're going to introduce Valora, which is our new mobile wallet launching very soon. And then for the developers, we're going to talk about how you can build on both Celo and Valora. So first, what is Celo? I think first we want to start with Celo's mission. So our goal is to build a financial system that creates the conditions for prosperity for everyone. That's a very ambitious goal, and so we took a pretty ambitious approach towards reaching that. We've taken a very full stack approach towards building this project. As you can see at the very bottom, we have our own layer 1 blockchain. This is a fork of Ethereum using the Go Ethereum client. But it is our own blockchain, completely separate, with its own history and network. On top of that blockchain, we have a bunch of core contracts which govern the Celo protocol, and that's kind of the protocol layer. Our smart contracts serve in Solidity, and you can see how there's a tight interface between both the contracts and the blockchain. On top of that, we also focus on the application layer, which I mentioned, our mobile wallet. And the reason that we took such a full stack approach is because we wanted to build a really compelling end user experience. We felt that only by designing from top to bottom with a product experience in mind could we deliver an easy to use, financially inclusive system. So what is the Celo platform? I'll dig in deeper here later, but I think there's a couple things to highlight. First, we're proof of stake. We use a validator set. Right now there's 100 validators live on the network. It's programmable and EVM compatible. As I mentioned, we're a fork of Ethereum, and so any contract that you can deploy to Ethereum, you can also deploy to Celo. Another interesting bit about the protocol is that we have full on-chain governance. So that means that you can change things like the number of validators and a bunch of other interesting pieces of the network just through voting on chain. Just to look back a little bit at 2020, which has been a year that I think no one has expected. We started with our great Celo stakeoff. That was our incentivized testnet. And so that was to kind of recruit and help our initial set of validators get started. With those initial set of validators, we launched the Celo network in April, which included our native Celo asset. And then just last week, we launched our stable value currency, the Celo dollar, and the stability protocol on top of that, which keeps the Celo dollar pegged to the US dollar. As you can see, we're almost to the Valora mobile wallet launch. So it's been an exciting year, and I can't wait to show you the mobile wallet when it's live. One of the things that we believe is really important as we've built Celo is user research. As I mentioned, we want to build something that's accessible to everyone, and how can we build that thing if we don't have everyone's opinion? So we spent time as a team going around understanding the needs of people who are financially excluded, and how what we're building can help them. That research has really informed how we design the Celo protocol. And I'll talk about a couple of ways that what we've done is really unique for mobile. As I mentioned with the launch of the Celo dollar, the Celo protocol allows for multiple stable value currencies. We think this is really important for usability so that users don't have to worry about the price volatility of whatever asset they're holding. We also allow users to pay for gas in multiple currencies. It can be confusing to understand the difference between two different assets that you might hold and why you have to pay with one to transfer another. And so we've kind of simplified that experience for our users just by enabling payment with multiple currencies. We have a lightweight mobile identity protocol that makes it easy to find other people on the network so that you can send and receive money from them. And then the last piece is the ability to sync quickly to the network in a trustless way using our ultralight client, so that mobile devices can participate in the network without relying on a centralized hosted service. So the first bit, as I talked about, is the Celo dollar, or CUSD. It's a stable value currency pegged to the US dollar. So we want anyone who wants to exchange one Celo dollar should always be able to get one fiat US dollar. There's a couple types of stablecoins that you might be familiar with. And I think the important thing to think about here is how they're collateralized. So first I'll start with Tether. That's collateralized with fiat currency off-chain. There's a bank somewhere that's holding US dollars, and then there's a corresponding blockchain, the Tether blockchain, which has an amount of Tether USDT that's equivalent to the amount of fiat currency held in the bank. Unfortunately, that's a pretty centralized system, and it requires trust of whatever entity is holding that fiat currency in the bank. The second is collateralized by crypto assets. So many folks here might be familiar with Maker and their stable currency DAI. That stable value currency is backed by crypto assets on chain, Ethereum, and that enables DAI to hold a peg to the US dollar. We believe this is a pretty complex system and requires a deep understanding of CDPs and the Maker system in order to understand how it works. There's also algorithmic stablecoins. Some of you might have heard of Basis, which uses seigniorage shares, and that has no other asset backing, but just uses a algorithmic supply and demand of a currency in order to keep the price stable. Celo uses a hybrid of both the crypto-backed and the seigniorage share style protocol, which we believe is a really nice compromise that allows us to both scale the supply of Celo dollars well, but also keep a strong peg. If you're curious about learning more, I'll talk a little bit more, but there's also a stability white paper on the website that you might want to check out. The stability mechanism has a couple pieces. First is the Celo reserve. That holds the reserve of Celo, as well as other crypto assets that backs the Celo dollar and other stable currencies. Next, there's oracles, and that's required to report the price of Celo to US dollars. And that is sourced from exchanges. By adding that price on chain, the reserve can work to keep the supply and demand of Celo dollars constant. And the last piece is what we call CP Dodo, or our exchange. It's a type of automated market maker exchange that allows anyone in the network to trade between CUSD and Celo, and eventually other stable currencies. You can learn a little bit more about the reserve. We have a reserve website, and that tells you exactly how much Celo is in the reserve, as well as other crypto assets right now containing Bitcoin and Ethereum. You can also take a look on GitHub and see all of our contracts, which I mentioned are open source, so you can see exactly how the reserve works if you want to dive a little deeper. The next feature of the protocol that enables mobile users, we think really well, is allowing users to pay for gas in a stable currency. As we went into the field and started doing some research, we had a lot of questions about how do I pay for transactions. We experimented with using words like security fee or different kinds of fees. And then also folks were confused about the difference between Celo dollars and Celo, formerly known as Celo gold. And that kind of led us to think a little bit about how we could simplify the experience for our users. And that led to a change in the protocol, adding a fee currency. As I mentioned, we're a fork of Ethereum, and this is one of the fields that's been added to our transactions. This fee currency can specify which other asset on the chain that someone would like to pay for gas in, or if it's unspecified, then the transaction fee will just be paid in the Celo native asset. We think this really simplifies the mental model for users so that they don't have to worry about holding multiple different currencies. If you want to transact in Celo dollars, you can just pay for your transaction in Celo dollars. The next piece, as I mentioned, is the lightweight identity protocol. That enables users to map their phone number to an address to make it easy to discover other users they might want to transact with. So a little bit about how this identity protocol works. This is the attestation flow. So a wallet user who wants to verify their phone number will first request an attestation in a smart contract. That smart contract will use a pseudo-random function to randomly select a validator. That validator is revealed to the wallet user, and then the wallet user can reveal the phone number at which they wish to receive the text message using our attestation service. So validators are running the Celo blockchain, but then they also run this attestation service, which enables them to verify user phone numbers. As I mentioned, the validator to send the text message is randomly selected from the current set to prevent any collusion between validators trying to map a specific phone number. As the wallet reveals that phone number to the attestation service of the corresponding validator, the attestation service will send a signed text message to the wallet user, and then the wallet user takes that signed text message and sends another transaction, completing the loop and proving that they are the owner of this phone number. So anyone who might have that user in their address book will be able to find them and send money. Now you might be wondering, how can we ensure that phone numbers remain private? It's an important concern that if someone were to try and, say, scrape all of the existing verified phone numbers, that could potentially lead to phishing or SIM swaps or other dangerous behavior. So what we've built to counteract that problem is a phone number privacy service. This service uses a verifiable oblivious pseudo-random function to generate a unique salt per phone number and rate limit queries. It's a little bit of a mouthful, so I'll explain a little bit in a simpler way. So as a wallet user who wishes to verify their phone number, what you want to do is to obfuscate your phone number with a salt. And so obviously, if you add a salt to your phone number, the hash of those two things as the identifier, it's much harder to guess and scrape the phone number. So in order to get that salt for both your phone number and other users' phone numbers, we use this phone number privacy service. So first, the wallet user blinds their phone number, which is a cryptographic function which just ensures that none of the operators of this service are able to discover the phone number of the requesting wallet user. Then, using a combination of multiple different service providers, none of whom have enough power to discover the salt for any individual phone number, the wallet user is able to request the salt for their corresponding phone number, use the signature aggregation of multiple different phone number privacy service providers, and then get back a salt from which they can use to in their mapping. Likewise, if a user wishes to look up the phone number of another user to see if they're on the network, they can query this phone number privacy service. The important piece here is that those queries are rate limited so that no one can scrape the database of all phone numbers. Then we ensure that there's both there's the usability of being able to discover people, but also the privacy is, we respect the user's privacy. The last piece here is the ultralight client, and that enables fast syncing to mobile devices. As I mentioned, thinking about building a global blockchain, we want this to be accessible to everyone. And so this might lead to some concerns that people in Silicon Valley aren't familiar with or don't usually think about. Things like intermittent data access, difficulty charging, older devices, or lesser technical fluency. And so when thinking about designing our protocol, we wanted to ensure that there was a path for everyone to use it. That's why our protocol doesn't require syncing the full blockchain or even the full chain of headers. as I mentioned, since Celo is a proof of stake network, there's a set of validators who are responsible for producing blocks. The validator set can only change on an epoch, and an epoch is just a set number of blocks, of consecutive blocks. Right now, there's an epoch about every day on the Celo network. So instead of having to sync the entire blockchain or the entire header chain, a light client only needs to sync the header for each epoch block, which contains the validator set. Then they're able to trustlessly verify that they have the true blockchain from the beginning without requiring every single block or every single header. This enables a light client to quickly sync up, even if they haven't been participating in the network before, and still not rely on a centralized hosted service in order to participate. We're also working on an improvement to this protocol that will allow users to sync without even the entire epoch header chain. And if you're interested, I recommend you take a look at Michael's talk on Plumo. This uses zero-knowledge proofs in order to allow light clients to sync to the latest chain state without even requiring every epoch header. So that brings me to what we've built using this protocol. And I'd like to introduce Valora, which is our mobile wallet launching very soon. Valora has been in progress the entire time we've been working on the Celo protocol, working hand in hand to make sure that as we work to ship this network and build this protocol, we understand the restraints and the concerns of wallet users, and we'll be able to build a network that's accessible. So we'll talk a little bit about Valora architecture. So on the UI level, we use React Native. That enables us to ship the same code to both iOS and Android. All of our UI code is written in TypeScript, which we think provides for more security and an easier developer experience. The middle layer is our SDK that we call Contract Kit. Josh will talk a little bit about this later, but the SDK makes it easy to interact with any of the contracts running on the Celo network. And then the last piece is the Celo blockchain actually running on the mobile device. So as I mentioned, the Celo blockchain is written in Go, and it's compiled with a tool called Go Mobile, and that allows us to actually run the same blockchain code on both iOS and Android phones. And that ensures that the phone can communicate with the network using that same code. So as we're building this, we thought a lot about how we can simplify this application as much as possible. How can we give people access to the financial services they need without needing to understand a ton of complex information? So I'll start with kind of our onboarding flow. Now, I'm not sure if anyone else remembers this, but I remember when I first started using Venmo and got invited to it, I was actively recruiting my friends to start using it. I would send them some money and say, hey, when we're at dinner and I'm not going to put my credit card down, I'm going to send you $20 on this app and you got to install it because it'll make your life way better. Unfortunately, with existing cryptocurrencies, there's no real way to do that, right? Because you can't send someone money without knowing their address. What's great about our lightweight identity protocol is that it solves that problem, and I'll tell you how right here. So if you're inviting someone to the Celo network, what you'll first do is generate a new private key and transfer a little bit of money on it. This money is enough to verify. And so then you'll text that private key to whichever person you're trying to invite to the network. So that person will take the small amount of money on the invitation private key. They'll generate a new private key in their app, transfer that money, and then use that small amount of money to pay for verification. So then they have a new verified account. And the last piece is that when you initially wanted to send someone money, you can actually escrow a larger sum of money with their phone number and that private key that you sent. So only after verifying their phone number are they able to withdraw money. So if I wanted to pay you back $20 for dinner, I'd transfer a little bit to that private key. I would escrow the rest of the $20. And then only after verifying would you have access to that $20. We think this is a much more secure experience than sending private keys around, but also provides really great usability and the ability to invite new users to the network. As I mentioned before, if you're curious, we'd love for you to take a look at our escrow contracts so you can understand a little bit more about how it works. There are a few other features that I love to talk about too in Valora. One of them is key storage. So we believe that while it should be non-custodial, there should be no central entity that holds a user's funds unless they want to. And so we designed Valora such that users are the only people who have access to their private key and funds. This is important thing to worry about though, right? Because obviously we want people to keep their key safe and we don't want anyone to be able to take a user's money. And so what we've done is encrypt the private key using both a client-side generated pepper that's random as well as a PIN. So that even if someone is able to get a file system access to the mobile wallet, they will not be able to unlock the phone to send funds anywhere. We also have spent a while trying to make sure that we educate users about how to custody their account key, as we call our backup phrase that you might have heard as well, because that's really important in order to be able to keep access to your funds in case you lose your phone or anything like that. Another feature that we built because of our experiences out in the field is Data Saver. So even though we have made the light client as light as possible in terms of syncing block headers, in some cases the latency and the network conditions are just so bad that it's impossible for a user to use a light node. In that case, we enable people to still keep their keys on their device, but use a hosted full node in order to communicate with the network. This we found gives people who otherwise wouldn't be able to access the system the ability to access it. And then the last piece, as I mentioned, is you might have heard me talk about CP Dodo and the stability protocol. Well, we make it really easy for Valora users to exchange between Celo dollars and Celo to participate in the stability protocol in the app. And that's again using that contract kit that I mentioned before to make it really simple to interact with the contracts. A couple lessons learned from spending some time building this mobile wallet. I think the first one is, as I mentioned, full stack is really hard. Many layers means that there's many places for errors. And especially in the early days when we were developing the protocol quickly, it was difficult to keep a stable environment, to keep up with changes, and to make sure that we could deliver that wallet experience that we wanted to. However, I think that trade-off, as I mentioned, is really worth it because we can develop a product experience that's really compelling. There's no, we're dependent on this thing that we don't control, or we have to wait for longer blocks, or, it just gives us the ability to iterate quickly and to kind of work on a product experience we're proud of. The second piece is that good async handling is your friend. As I'm sure folks who have developed a blockchain before, things might take a little bit longer than you're used to, and it's really important to have good asynchronous handling. Since we use React Native and TypeScript, we're able to use a library called Redux Saga, and that really helped us with control flow, being able to block different things on network status or sync status, but still have a simple developer experience. And then the last piece, as I mentioned, is that user research is really key. Even though we had some ideas about how we wanted to build things and what we wanted to build, we need to test our assumptions with real people in order to understand what was true and what wasn't. I think that there's no way we would have built the product experience that we ended up with today had we not spent time understanding the needs of people around the world. So hopefully that was a good bit of information about what we've already built. But I'd love to turn it over to Josh to talk about, as a developer, what you can build.
All right, thanks a lot, Connor. So to make it easier for DApp developers, we created the mobile first SDK. And this is really what we used internally to build the Valora app. The two pieces being the contract kit that Connor mentioned, as well as the DApp kit. The DApp kit's a little bit more for advanced usage, but I'll get into that in a minute. So we designed the Celo SDK from the ground up to make it easy to build mobile-first apps. Connor, can you just go back one slide? Yeah. And the Celo SDK offers several advantages over similar blockchain development tools because Celo has several more primitives available that Connor mentioned. So Connor mentioned the exchange, and we have easy integration with Celo assets, being the Celo native asset and the Celo dollar. The contract kit comes with core contract wrappers that are already initialized, so you don't have to initialize a set of contracts every time you set up your application. And we have easy access to the lightweight identity layer that Connor mentioned that maps phone numbers to addresses. And also easily paying transaction fees in alternative currencies. So you don't have to use the Celo native asset to pay transaction fees. You can use alternative currencies, and this is easy to implement using the SDK. So as we add new currencies that are approved for paying transaction fees, this will be easy to integrate into your application. So you can go to the next slide, Connor. So currently the Celo SDK has two parts, the contract kit and the DApp kit. And the contract kit works at a little bit lower layer. It's like a wrapper around the Celo core contracts. So it makes it easy to access things like the stability mechanism, the validator sets, the oracles that are helping with the stability mechanism, and accessing the identity layer. You can import contract kit into your project and have quick access to the core contracts without having to initialize any of these contracts. You can just access them. They're right in the JavaScript objects. And DAppKit is more like an interface between applications that are built on top of the Celo protocol. So it's kind of at the top layer. It's currently designed to interface with the Valora wallet, and the Valora wallet is acting like the user's connection to the underlying Celo protocol. So reading and writing to Celo can be managed by Valora using the DAppKit, so you don't have to manage connections, user accounts, or signing transactions yourself. You can just use the DAppKit for this. So as I mentioned, contract kit wraps the Celo core contracts, including the core ERC20 contracts, in an easy-to-use interface. So as Connor mentioned, Celo includes the EVM as the execution engine, so our core token contracts follow the ERC20 standard. And contract kit is currently written in TypeScript, so it easily integrates with any JavaScript or TypeScript project, and we're hoping to support more languages soon. And we welcome any contributions from the community to either contract kit or DAppKit. As Connor mentioned, this is a fully open source project, so as you guys start playing with this, we'd like to hear what you are interested in adding, and would like to help you add it as well. So DAppKit relies on the contract kit for much of its functionality. DAppKit makes it easy to access some of the core features of Celo, such as the stable value currencies in a user's Valora wallet. It makes it easy to specify which currency a user should pay transaction fees in, and to look up Celo verified phone numbers and accounts in a specific user's contact list. So this makes for a very different user experience than what you might be used to developing on other blockchains. We built DAppKit in TypeScript as well, and we've created example apps written in Expo. So anybody with web development experience can jump in. You don't need too much mobile development experience to get started. But the DAppKit will be comfortable for mobile developers that are familiar with React Native, and Expo makes mobile development with React Native similar to a more traditional web development experience. But it does take some resourcefulness in getting used to if this is a new framework for you. So if you haven't heard of Expo yet, it's super easy to get started with. And as you get started building on DAppKit, you'll you'll get really familiar with Expo and React Native as well. All right. Yeah, so this is a short demo of the DApp kit in action. This is our example DApp. So you can see on the main page, we ask users to log in. There's a few buttons. It defers to the wallet for the user to log in, and the wallet asks the user if they should sign in. And once they're signed in, you can see their account, their phone number, and their balance. It's reading a smart contract, and it just popped up. It's a little small there, but it popped up, and it just says hello with a couple wave emojis. That's the name of this Hello World contract. And now we're going to ask the wallet to update the name of the contract. So this is deferring to the wallet to actually sign a transaction and send it to the network. And we're just updating it to Hello SF Blockchain Week. And we can see that the transaction already executed on the testnet, and we read the contract name again, and it's updated to Hello SF Blockchain Week. So that was a pretty quick run through of the example, but you can download and explore this example, look at the code, and modify it yourself. It's a good boilerplate for starting your own project and just playing around with DAppKit and Contract Kit and getting started on the AlphaHorizon test network. But here's an example of a DApp that we built using DAppKit with a similar boilerplate as the previous example we just showed. This is a saving circle DApp. A saving circle is a strategy to help a group of people save money, where they can contribute and withdraw funds at different times. So here we're showing someone withdrawing the group's savings after it was built up. So you can see that a call is initiated to the smart contract. We have to sign the transaction in the wallet and pay for gas. Luckily, we can pay for gas in Celo dollars. And then we just have to approve the transaction in the Celo wallet. So once the user approves the transaction, the funds from the saving circle are deposited directly into the user's wallet, and then the screen will switch back to the DApp. So we're just deferring to the wallet for some actions based on the preference of the developer of the application. So the application developers don't have to worry about managing the accounts, the keys, or these transfers. It's just handled by DAppKit, making it really easy. So yeah, going on to some of the other projects that we've seen built on Celo in the past couple months. In some hackathons and incubators, we've seen Impact Market working on a universal basic income game. That's pretty cool to see. We've seen Bienvenir helping refugees get financial support when they move to new countries and they don't have access to existing financial or banking infrastructure, and they need access. PesaBase is building an integration with M-Pesa, which is a huge payments network in Africa. So helping people in Africa get access to financial services, as is DunyaPay. They're helping with low-cost money transfers in sub-Saharan Africa, and also Multiply Charity, which is increasing transparency and impact of donations with alternative currencies, currently working on Ethereum and Celo. So yeah, going on to what will you guys build? Just from my perspective, with teams I've been working with, looking at other blockchains and kind of the way things have been going in the space, I'm really excited to see decentralized financial applications built on Celo. Ethereum has seen a lot of activity in the decentralized finance space, and what is possible on Ethereum is also possible on Celo. As Connor mentioned, Celo is still really new. We haven't seen a lot of development here, so it's a green pasture. There's a lot of potential here, and I'm excited to see what happens, particularly things around allowing users to use Celo assets as collateral for loans, or users being able to earn interest by providing loans to other users in the Celo ecosystem. I'm really excited to see bridges to other blockchains. We've seen stablecoins really explode on Ethereum over the past few months. And Celo has a unique solution to the stablecoin problem. There's the problem between decentralization and centralization and how those assets are collateralized. Celo is kind of unique in this domain. So how does the Celo dollar fit into this decentralized finance space? This is to be determined. And I think, again, there's like a lot of potential here in terms of what's possible. And I think developers are going to be pivotal in deciding which direction this goes. I'm excited to see advanced user wallets. So as Connor mentioned, Celo is focused on user experience from the beginning, but there's still a lot more work to be done to make these systems even more usable. And I think keyless wallets or smart contract wallets are an underexplored area of research and development. And yeah, I'm excited to see what people come up with. Also, DApps that leverage lightweight identity in new ways. This is a new primitive kind of in the blockchain space. I don't know of another project that has a robust lightweight identity layer. Valora is using it to look up friends and send them money. And this is an obvious first use case for a phone number-based identity system, but there's a lot of potential here. It's, again, an underexplored area of research and development. And I think it's easy to imagine a future where the lightweight identity layer becomes essential beyond just sending payments to build more robust digital identities. And it's interesting to start thinking about what digital identities might look like with advanced user wallets. So yeah, I invite you guys to help us explore these avenues and like see what we can build, because there is a lot of potential here. So yeah, I've got one more slide just inviting you guys to connect in a couple different ways. Celo.org/developers is a great site. Celo.org generally has a ton of great information. You can sign up for our newsletter there in the middle, and then also on Twitter we're at CeloDevs and also at Celo.org. So yeah, I think that's it, and thank you for your time. This has been great, and as Connor said, we'll be around for question and answers, and come visit our virtual booth.
Yeah, we'll be doing a little.
It started simple. A token, a symbol of hard work, of skills, for trust between people. Money was meant to be exchanged for things created and services provided. It takes many forms, both plain and shiny, honoring leaders of the past and those leading us into the future. Somewhere we lost our way. People waged wars over it, big and small, concerned more with growing interest on $244 trillion in debt than growing communities. And many people are left out, 1.7 billion invisible, left behind and underserved. But what if money were more accessible to everyone? A universal symbol for essential needs, for empowerment and connection. People, communities, entire countries prospering. What if money were all of this? What if money were beautiful?
Thank you, Connor and Josh, for the overview. We're excited for Celo and Valora's future. For those of you that are just joining us now, if you have any questions during the talks, please feel free to ask them in chat. Our speakers will answer them accordingly. Now for our next talk, we will have Paul Gadi, CTO of OP Games, give a presentation on decentralizing video games. Paul, the floor is all yours.
All right. So, good morning, everyone, or good evening, wherever you are. Today, I'll be talking about decentralizing video games. Decentralizing video games is kind of a big topic, and it's a bit um, geared towards my specific industry, which is in video games. But it applies to other industries as well, aside from the game industry. So, I hope you'll take away something from the talk. So a little bit of a background on me. My name is Paul. I'm the CTO and co-founder of OP Games. And OP Games is my startup. I've run a few startups in the games industry and exited one of them. And through being in the game industry for quite a while, you kind of see how the industry kind of moves in cycles. And I'll be touching on that a bit when we start, and that's kind of like a background, or like the overarching background of this talk. So it's good to begin by taking a little of a step back. So when we look at the video games industry and the cycles that it moves in, we know that the video game industry is kind of a newer industry than most, but it also moves in technology and market cycles. And right now, when you look at the video game industry, you can see that we're in a very mature market cycle wherein there is still some growth, but there are hallmarks of it becoming a very challenging market, which isn't very conducive to newcomers. And we will see also how this kind of market is kind of also ripe for people to innovate on. So as a mature market, we can see that the competition in games is kind of very fierce right now. So on the left side of the slide, you can kind of see one of the more extreme years where competition was very fierce. In 2017, about 2 or 3 of the games were able to make just about the top 80% of the revenue. So there's a very sharp power cycle, very sharp power curve when we look at how revenues are distributed in the industry. So this competition isn't just obvious in the graphs. There have been also surveys with game developers, as you see here on the right side of the slide, that the main concern of mobile game developers around the world is competition and how many games there are out there in the market. So being a new game developer is kind of really challenging in a very mature market. And it's important to note these two things also, these two other concerns that game developers have, which is the rising UA costs, UA meaning user acquisition, rising marketing costs, which is the cost of getting your game discovered, and the amount of free content is also important. So you can kind of see that it's kind of a race to the bottom to get the revenues. So I'd like us to take note of these two things, the UA costs and marketing costs, because this is kind of important to this next slide, wherein we see most of the monetization methods of games has actually centered around ads and in-app purchases. So in a very mature market, you kind of see that value consolidates around platforms. And in the case of games, we kind of see it consolidating around ad networks because they're the ones that handle the ads, and app stores through which all of these in-app purchases flow through. So in a very consolidated market, we can see all of the value going through these platforms. So that when you look at this diagram, you can see that ad networks and app stores, they are the ones that are the arbiters of value in the ecosystem. So whenever a developer needs to transact with the player, all of these has to first go through these app stores. Whenever a player wants to get something for the game, it has to either go through in-app purchases, or they can either watch an ad so they're able to get something back in the game. So in a very mature market where platforms have kind of consolidated the value, it's these platforms that now define the rules. They're the ones that tell you, are we able to use crypto in our ecosystem, for example? So in this case, we see that most of the app stores don't really care to add other alternative monetizations. And this makes sense because when you're in a very mature market and the platforms are the ones that are really controlling all the value, they're kind of disincentivized to improve because all of the value is now to their benefit. So that this is something that we call platform lock-in. And when platform lock-in happens, it kind of disincentivizes the improvement of the platform. So in the game industry, being a very mature market, you can kind of see that there's a clamor for change already from several sectors. From the player side, here on the slide, you can see that these are two player testimonials on how they're kind of they're not very happy about the industry anymore. The first one is from a player who's playing this game, and he's saying that he needs people's help because he's having major mental issues around not being able to control himself from paying for in-app advertisements. The other one here is about a player saying that games right now are really pay to win, and he tries to harken back to the time when games were all about achieving things or about the narrative rather than paying to be able to beat your opponent. So there's also clamor for change aside from the players, from the developers. So here on the middle of the slide, we can see the top games that are making revenues in the past year. And these games, they haven't really changed in the past 5 years. The past 5 years is the same games just moving up and down the charts. So developers, these are the developers that are making money, but there's a very long tail of other developers that are barely breaking even or not even making money with their games. And then the last part of the slide, we see that even government is starting to get involved. That they see that players aren't happy. It's being a bit exploitative to them already. And some of these game systems are starting to look like gambling. And in Belgium, they already banned a way of monetization of these games. So we can read down here also that gamers are actually supportive of the ban. So there's this clamor of change from the players, from the developers, and even government. But the platforms really won't be incentivized to change it. So we're kind of stuck here in this very mature market. But as technology cycles go and market cycles go, as we see that the games industry becomes very mature, this is also a time when it's really ripe for disruption. So we've seen this before in the game industry. We've seen this happen, for example, with the rise of social games. We've seen this happen when PC games started to migrate, or game developers started to migrate from PC over to mobile. So this is a natural cycle. Platforms really will consolidate value around the market, but this is exactly the right time for us as builders to look at where we can go in, try to look at what the market is asking of us, and try to build around that. So being in this space, I believe that when we see the value that Web3, blockchain, and all of these technologies and movements around decentralization, we can see that these are the beginnings of what would be able to change the platform economics. And I'll discuss how we could possibly use these coming technologies and movements to be able to decentralize games. So this is a big question. So how do we decentralize games? And it's and I harken back to Amara's law, which says that we always underestimate the value of a technology over the long term. And we are right now in a very early stage in decentralization in games. And we don't really know how it will look like yet. We don't really know the final version of how a mature decentralized game will be. But we're kind of starting to see how this will go based on the technologies that are coming up, and also some of the similar movements around decentralization that are also building with Web3. So, so this is a possible playbook that we can take a look at. This is based on what the platforms are strong at right now, which we can possibly disrupt with our current Web3 technologies. So we'll see identity, data, and asset ownership as three things that these platforms control. And these are the specific areas where we can start taking a look at how to disrupt how we can disrupt their control over these items. I'll discuss each one of these one by one, and then we'll go through the next one more around the movements of open source and co-op. So regarding identity, usually when you play a game or when you download an app, you need to log into a certain identity, to a certain identity account. So this might be the Google Play Games, for example, or a Facebook login. And as users and as players and as developers, we've kind of been used to this paradigm. It's very convenient for us to just use our login on Google, or for us as developers to just use the same structures as Facebook has in identifying our users. This is actually not helping us in the long run, because it kind of limits us in developing, because our players are stuck in this closed ecosystem. So a way to change platform identity is to use the current technologies around crypto now, which deals with decentralized identity. So an example here is Web3 model, which is a protocol, an open source protocol that allows us to use any of the supported wallets to be able to log on to certain services. So we see here that Web3 modal can be used to log on to MetaMask or any of these other third-party services. So one thing to take note of also is this might be a way to decentralize and allow us to define where identity is being custodially handled. But we need to be aware also that this is a certain kind of platform in itself. So we need to not build on the platforms, but build on the protocols that Web3 modal is building on. So after identity, we take a look at data. So platforms have usually been the ones who control data in the video game industry. So you can kind of see this with, for example, cloud services. We see when you're playing a game, most of the data is usually stored centralized in a cloud service like AWS. And this data is usually not really this data is usually mostly monetized by the platforms, and there's no real benefit for players and developers. So if you have data on a server, it's mostly the developer paying for the service from Amazon. It's mostly them renting out the service where players can play their games. So this is kind of the status quo. We can't really see for now a lot of any alternatives to this. mainly because AWS has kind of the scale to be able to handle a lot of players, and they're the services where a lot of the tooling is built on. But we can kind of see some other alternative ways to do this now with certain protocols that are coming up. A good example of this is IPFS, which is it's a peer-to-peer hypermedia protocol wherein instead of storing the data in just a centralized server, we are able to store data across nodes. So these nodes can either be several other different servers. This can be even stored on the player, for example. So this kind of changes the way we store data and the way we value data, that instead of us renting out servers, would there be a way for it to possibly store the data on our player's side, for example, and possibly maybe find a way to monetize that on their end. So this kind of shakes up the current paradigm of centralized data that the platforms currently benefit on. So aside from identity data, the third part is asset ownership. So in games, usually a lot of the revenue is taken whenever someone purchases an in-game item or an asset or any item that they own in the game. So in these cases though, a lot of the times, the only way for a player to buy these items is to go through the game's platform. So, and there's no way to trade these items around. There's also no way to take them out of the ecosystem of the game itself. So for example, you're playing a game, you buy an item, and the moment that you wanna change your game, or the moment that you don't want to use your account anymore, that item is trapped there. But that item has actual monetary value. It has actual value that people have worked to be able to acquire that item. So even if the item is closed in an ecosystem and isn't really part of a crypto system, it still has actual monetary value. So an alternative to these items that are locked inside game universes is the centralized asset ownership. So you kind of see this happening now with the start of NFTs. You kind of see items that are being created outside of their game universes. So when you create these items based on a standard such as NFT, they aren't tied to a specific game. They are able to, you kind of unlock their value and not just have them be useful in a very small network, but they're able to be used across networks. And this also allows them to build new opportunities or even jobs around these new asset classes. So aside from players, we might be able to have people create these items, for example, or people just collect these items around different universes. This kind of opens up the economy to something bigger. So to kind of recap on these three things, if you wanted to decentralize the games industry, there are three ways that we could start doing it. One is through identity, data, and then through asset ownership. But decentralization is nothing new. It's actually a movement that started even before Web3. We can kind of see how platforms consolidating value as something that isn't really conducive to a lot of players in an ecosystem. And we can look at two other sources of two other movements that are very, very good references for us to learn how to disrupt these platforms. So when we look at these two platforms, it's kind of like standing on the shoulders of giants, because these two movements of open source and co-ops have been here for a while, and they have been able to successfully disrupt platforms. They've been able to successfully decentralize certain economies. It's really good to see what they have done well and apply that to any of the industries that we're looking at. So to start with, open source really is a really good model for when we're looking to disrupt something. For in the first place, a lot of these platforms rely on us building on their closed ecosystems. So for example, just when we're making a game relies on a lot of technology, and a lot of game developers have been used to making games on engines such as Unity or Unreal. And what game developers usually don't realize is these platforms are ecosystems. These game engines are ecosystems in themselves. And by building on them, we kind of limit ourselves on building on the platform's rules, building on the platform's economics. So, but if we look at open source, there are actually a lot of other tools that are mature enough that would be able to handle what these monolithic engines are doing. So one important point also is, aside from building an open source, we need to consider building on the web. As we've seen, the platforms usually have their own way for developers to deploy or for developers to monetize, which is through ads or the in-game purchases. But the web is an open area to deploy your game. You can just put it up on a website. You can also make use of all of the groundbreaking technologies that are being developed right now on the web, like XR for augmented reality. So the web is actually a good way to start building new economies on top of. And we don't, since we're used to app stores and ad networks, that doesn't mean we can explore other ways of doing so. So one good example of a game engine is Babylon.js. Babylon.js is a very mature and sophisticated 3D engine where there are already has already successfully used to build several good games. Another engine that we can possibly use is Phaser, which is very optimized for 2D. It's easier to learn, and there's a really huge community of game developers around it. And aside from game engines, we can actually also use open source to build the things behind the hood of a game. For example, multiplayer servers or any other services that our developers need. So a good example of this is Coliseus, which is an open source multiplayer server, and it's built mostly on JavaScript. So this is another important point also. JavaScript has a very, very big developer base, and it also has a very vibrant ecosystem of people developing modules. So if you're building a game on JavaScript, it's easier to put all of these open source modules together and really build a game that doesn't need to use all of the native properties of a mobile app. You can actually just build it on JavaScript on the browser. So we have open source as the first movement we can take a look at to kind of shake up the platform economics of an industry. But another one that's been also brewing is platform co-ops. So platform co-ops have been there a while. You can kind of see a lot of the hallmarks of decentralization there. So if you want to see real concrete examples of people creating new economies versus the platforms, a good book to read is Ours to Hack and to Own by Trevor Scholz and Nathan Schneider, and to go to metagov.org, which shows a lot of how people are thinking about when governing virtual worlds. So with these three things, changing identity, changing asset ownership and changing data, and then looking at open source and platform co-ops, we can kind of start remaking platform economics and have a strategy on really how to decentralize games. So a call to action to people now, something we can do right now very concretely, is we need to be able to create sort of like a convergence stack similar to what or Unity has done, LAMP has done for web development, and Unity has done for game engines. So Jamie Burke, the CEO of Outlier, who is one of the good thinkers in Web3, says that when people talk about fast adoption, they typically mean 99% of consumers. So we need to improve upon Web2 apps. They need to be faster, experientially better, and possibly more private. Mass adoption will only come when we have found ways to abstract away the complexities of Web3, making them invisible to the average user. So this is what we as developers need to do. And this is also something that us in OP Games are trying to build. So if you're interested in helping us build this invisible protocol, in us building this convergence stack, check out game3js.com, reach out to us in these links, and we'll be very glad to build these technologies with you and to explore the new economies that we can build when we decentralize video games.
Thank you, Paul, for your talk. It's great to see gaming as a direction we can move towards in crypto. For those of you that are just joining us now, if you have any questions during the workshops, please feel free to ask them in chat. Our speakers will answer them. For our last talk, but definitely not least, we're happy to have Sean Braithwaite, CTO of Informal Systems, give a talk on the essentialism of light clients. In this talk, Sean will go into the importance of light clients on Tendermint and how it allows for validation without having to store the entire history of the blockchain. Sean, the stage is all yours.
All right, hello. My name is Sean Braithwaite, and I work at Informal Systems on the engineering side. We do formal verification of distributed systems. Most of the stuff we do is in the Cosmos ecosystem right now, but we're looking to do collaborations with the greater cryptocurrency scene. Today, we're going to be talking about the last thing that we did, which was write a light client for Tendermint. And we wrote a light client in Rust, and we built it for formal verification. So this is the first software artifact that released as a product of our process. So we're pretty excited. We have the Tendermint RS repo that's available on our GitHub, which is eventually going to be a full node of the entire Tendermint protocol. But right now, what we're releasing is just the light client. So you could go and play with that and compare it to the Go implementation if you want. Which might lead to the question of like, why would we write another one? And why would we write it in Rust? Well, the first implementation of Tendermint, which was very essential to launching the network, was not built for formal verification. And we wanted to try and build one that was. So before we talk about what we built, I think we need to talk about what the greater objectives of the ecosystem are. So Cosmos was planned to be the internet of blockchains to provide sovereignty and interop between finite state machines. And maybe a picture is the best way to look at it. So you can imagine that there are not one, but many blockchains, because that's actually what the world is, and that's actually what's in the picture. So for instance, you have Ethereum on the far right, and then Bitcoin on the left. And then you have the Cosmos Hub, which was the network that was launched, which is built on Tendermint PBFT. Then you have Agoric, which is another hub, right? So beyond the nodes, what is important is what connects them. So the vision of Cosmos that was imagined was to have a permissionless interop protocol called IBC. So IBC allows one chain to connect to another without an intermediary. So essentially you can do atomic swaps between chains. Maybe the easiest way to look at it is from the inside. So imagine you have, instead of having a multitude of chains, let's just focus on two for simplicity's sake. So on the left you have chain A, and on the right you have chain B, right? You can imagine that each blockchain is represented by a finite state machine, which is somehow replicated across nodes to serve as like internal logic. And what is important here is that these chains can be extended to implement the inter-blockchain protocol, right? To essentially process a special type of transaction that is particular to facilitating interop with other blockchains, or it's a set of transactions that is essential to interrupting with different blockchains. So one question is, like, if a transaction on chain A is destined for being somehow replicated and integrated on chain B, how does it get there? Well, this in the middle of the diagram with indexed unit 5, the relayer is responsible for effectively listening to changes on chain A and then relaying to chain B. But you could also envision how you wouldn't want to relay invalid packets, right? So essentially you need a way to verify a packet or a transaction before you relay it. So to do this, we have the light client verification protocol. And the light client verification protocol allows us to essentially verify state without sort of accumulating it. So without having the entire blockchain history. So in short, the light client verifies state using only headers. So the metadata, something that describes the particular parts of the state chain without the transactions themselves. You can imagine that this is somewhat essential, right, to a number of applications, the relayer only being one of them. Another application would probably be in running on low power devices. So if you ever wanted to essentially verify state as an embedded component to a larger application deployed on a mobile device, right, you would probably need to embed a light client. So I think there are a lot of other use cases that we could sort of envision, but it's kind of essential to the adoption of the ecosystem that we get this bit right. So let's look at how it works. So I think to understand the inner workings of the light client, you need to consider like the Tendermint consensus safety guarantees, right? So Tendermint is a proof of stake network, which means that there are a subset of the nodes in the network that are actually proposing and validating blocks. And these nodes essentially have to put something at stake before they can participate at that level, right? So they need to actually lock up some funds denominated in some unit, right? That says that if they were to commit malfeasance, like either by double signing or any other number of malicious activities, right? They could be punished. So they could be slashed. And you can imagine that the set of validators, a set of nodes that is responsible or responsible in general, but in particular at the risk of getting slashed, right? It's changing, right? So it's not always the same people who are voting. There could be new validators coming in and other ones rotating out. So if you consider how do you trust a changing set of participants. The easiest way to think about it is that if you participate rightfully with a majority of other people, right, then you could also be trusted. So you could imagine initiating from Genesis that you would form some set of validators that would be produced through social consensus, right? And then essentially you would follow the change of the validator set by maintaining the majority of the trusted, and then you could sort of move forward. So in the diagram, what you have is like 3 headers that are sort of increasing in time. So H1 would have some validator set, H2 would potentially have another validator set, and H3 would potentially have a completely different validator set. And you can imagine that from social consensus to H1, you could sort of rightfully trust them because it's in the bonding period. The validator set has not changed significantly enough that you would be skeptical of the people that are in there. Now, as H2 happens, it's possible that the people from Genesis, right, have decided to stop validating, right, but are still in the unbonding period, and in the unbonding period, you could still be slashed. So you've committed to stop validating, but you haven't stopped validating just yet, right? And then H3, which is sort of at the end of the unbonding period, right? You're in this phase where your funds are free and you can no longer be slashed, and therefore you should not be trusted. So what the light client protocol is doing is trying to figure out what it can trust based on the changes of the validator set. But it's clear that this is not just that this question about trust is somehow bound to how people can be punished. So one of the things, a lot of people look at light clients as sort of takers and not givers, insofar as they don't contribute directly to producing blocks, right? But one thing that our light client does, because of like the finality assumptions of our consensus protocol, that is assumed that like when a block is final, any change of values or any differing value at that height constitutes a fork. So we have this protocol essentially to detect forks that is conducted by our light client. So while the light client is consuming headers, trying to get to the most recent state, it's also comparing those headers between peers. So it won't just ask for a header from a single peer, it'll ask from multiple. And then it'll actually perform if those headers are different, right? So maybe there's a different application state, then it will actually perform verification to see where in the lineage of that chain did things differ. Now, the light clients can't actually punish the nodes. If they were to commit some kind of malfeasance, the light client could not punish them, but they can report them. So what the light client is responsible for doing is doing fork detection and also submitting evidence to the to a full node. So it doesn't submit to one, it submits to many. So the light client is therefore responsible for maintaining sort of a set of peers that it could, one, query headers from to update state, maybe in parallel, and two, performing fork detection, so seeing the difference, and then three, submitting any evidence of differing values at a similar height, right, to the full node for a completely separate protocol, right, called fork accountability. So you'd imagine that once the evidence is submitting, you're going to have some process of like, figuring out who is lying, and that can only be performed by the full node. But that's kind of like outside of the scope of this talk. But it's still pretty important that we get this protocol right, not just the protocol, but the implementation. You can understand how, in the context of IBC, right, relaying packets between chains might be very hard to diagnose because the receiving end will be a completely different blockchain, right? And also in the case of mobile phones, you can imagine how useless a system would be if it would to trust the unjust state, especially in a permissionless network. So the question is, what would be the value of an unjust system? Like, why would, if people did not trust it, right? If it didn't work, why would anyone bother participating in it? So in a lot of ways, with these public blockchains, it's pretty essential that we bake correctness in from the onset. And as a previous message, this is kind of really the motivation for Informal as a company, and the light client rewrite and Rust in particular. So what we wanted to do is not just design a spec, but a software artifact which kept pretty closely aligned with that spec over time. So we kind of took a completely different approach of making sure that our protocol was safe, it was lively, and that these properties, these invariants, would stay over time, and that required sort of like a multi-pronged approach. So the first thing that we did is specify this sort of in this English, this formalized English, like something that could be kind of extracted into an academic paper pretty easily. So easily, in fact, that we just submitted a bunch of papers with anticipation of publishing, at least to archive in the coming weeks. But what's most important in this is not the particulars. I don't know if it's feasible or even useful to kind of read the particular slide right now, except for these sort of indexed invariants, right? So all the things that we expect to be true, these like temporal properties, always true. Things that are sometimes true, some things that are never true, and things that are like eventually true. These temporal properties are like enumerated and indexed, right? And so the idea there is that we expect from the onset that these temporal properties will be like, one, the subject of conversation. We're going to negotiate and figure them out and probably iterate them over time, so it helps to have a reference, but are also expected to be represented in multiple forms, readable by computers. So one of the ways that we represent these temporal properties is, of course, in TLA+. So this allows us to essentially perform verification. For those not familiar with TLA+, essentially you specify a bunch of temporal properties, and then it essentially generates an exhaustive set of examples trying to figure out where those properties are violated. So it'll give you the output of this process, if, depending on how you see it, successful or unsuccessful, would be a counterexample of a case in which the things that you say is definitely not true. So this is critical to at the protocol level, like ensuring that what we think is true is actually true in a computable way, and has been kind of essential to us finding a lot of bugs. And so one of the things we did with the light client is essentially write the spec in English in TLA pretty much at the same time. So a lot of the abstractions that we came up in the sort of design phase, right, were ported over or back and forth between different representations of the protocol. And I guess like of all the representations, of correctness, probably the biggest one is the actual code itself. So I guess this is another, maybe not the most ideal screenshot because not all of it is important, but there are certain parts that are important. One important part is the last line on 147 that shows a little bit of Rust. So yes, there is actual a Rust implementation of this. That's what we're releasing, and that's what you could run on the network. But what the point that I want to make is that the indexes, the tags, right, that are mentioned in the English spec and then represented in TLA are also present in the code. And the format of the English spec that specifies like post and preconditions for individual functions are included as sort of predicates that are annotating the functions that they're specifying. So that means that if we run this in test code, we're going to get, or in test mode, we're going to get the same errors, right, that we would get in the spec in the actual executing artifact. So this is pretty cool, and is kind of essential if we want to take this idea of formal verification seriously, because correctness does not stop. Software is an evolutionary process. It's an iterative process, and it's going to change. And the question is like, what is the value of having a specification for an outdated or an outdated spec? It's kind of like the value of like outdated documentation. At one point, that that product, right? That either that documentation or that spec was an asset, right? But as the software process continues, it becomes a liability because you have to keep it up to date. So one of the things that we're working on are tools to help maintain alignment between English, TLA, and software artifacts. But all of this can be contributed today, and this is where we could use your help. So one of the ways that you could contribute to the process of developing Light Client and Cosmos in general, right, is to come work with us. That's one idea. Another idea is to run the Light Client, right, on the Cosmos Hub or other tenement-based chains, right, and actually performing fork detection. That means that you don't have to run a full node. You don't have to have like gigabytes of disk or terabytes, let's be honest, of disk space, and you'll probably start contributing the same day. So that'd be fantastic. Another way is with the code. So participating in this endeavor to formally specify distributed systems. If this is something that is interesting to you, we would love your contribution or your perspective. So thank you for that.
Thank you all for tuning in on the first day of our Developers Track. I hope you enjoyed the content we put out today. Please come back tomorrow for day 3 of Unitize, which will also conclude our Developer Track sessions. Rest up and be ready for another day of coding.